All right, good afternoon. So we start with the second session, so the afternoon session with Daniele Coslovich from Grenoble. So I let you the floor.
Yeah.
Thank you.
Thank you. So hi everyone, and thanks the organizer for the invitation. So I'm David Coslovich. I'm postdoc in Grenoble in France. And the idea with this talk is actually I'm not going to talk much about predicting dynamics of viscous liquids. I'm more going to show you some methods that are actually also not based on machine learning, more on the energy landscape of a glass. And with those tools, try to predict more plasticity in driven solids. And this work is done in collaboration with Idan Lerner and Geert Kapteins in Amsterdam and Lisa Manning and Giulia Giannini in Syracuse. I guess most of you in this audience are familiar with viscous relaxation at finite temperature. Here I'm more going to talk about mechanics, plasticity, so I'm even going to consider zero temperature, just taking a solid without activation and starting to deform it and trying to predict what's going to happen. And if you take a piece of solid and you will do that, so you will deform your solid, you will relax the energy, deform your solid, relax the energy, and follow the evolution of the system, you will see things like this. So let's say a bit like viscous dynamics, you will have some rearrangements in mechanics they call shear transformation zone, where really when you start to shear the system locally, some particle will undergo a small shear transformation and rearrange from one state to the other. And there will be some stress release across the system, and then that could lead, for example, for emergent collective phenomena like avalanches or strain localizations. And the same communities that develop sort of tools to try to understand patterns like locally favored structure or unfavored structure that will lead to viscous dynamic, they also use these tools or develop new tools to predict plasticity in amorphous solids. And so you have seen already in this morning a large variety of methods which are, for example, purely structural or machine learning based, but they're also part of the communities that work on other type of methods which are not necessarily purely structural, also require interaction between particles. So I can base on the potential energy landscape of a glass, some anisotropic indicator. For example, think about local shear modulus, for example. And even things that are not even local, where you will really have to deform your system to get some information about heterogeneity, like the residual plastic strain for the sometimes calls the local yield stress, where you will even take a piece of glass and every part of the glass you will shear it locally. So you will froze everything in a system, you will take a cavity and you will start to shear it in one direction. And you will not monitor the global stress and deformation, but really the local stress and the local deformation. And you will be able to measure for every patch of the particle how much stress I need to put in my system to see it yield. And when you apply this kind of methods for in a glass, even if you don't deform it, what you typically see. So my talk will focus on more like energy landscape, anisotropic indicators, and local yield stress. But generally, what you see is that in a glass you have weak region and some other regions that are more strong. So for example, this is the local yield stress in a given geometry. And orange and yellow colors, they show you regions that have small local yield stress. So it's region where I will shear it just a little bit and the system will already yield. And in blue, it will be regions that are very strong. I could deform it very long time and I will not see any plasticity. So that's maybe familiar for also for viscous liquid, where you have local or unfavored structure or locally favored structure that will promote relaxation in a viscous liquid. But in the case of mechanics, there also one thing is that here I'm showing you the local yield stress in one particular deformation, but I could do this thing in arbitrary deformation. And when you start to do this, what you realize is that in the context of predicting plasticity, you're not only looking you don't only want to have a scalar quantity, but really a tensorial indicators, because some defect that, for example, might be relevant for under simple shear might not be relevant for pure shear, for example. So you would like to have, basically, we will have to develop method to to find defects in glasses, so maybe individual defects. As you see, that's localized plastic deformation, so you are looking into at localized defects, not extended one. How to extract their micromechanics, because it will depend on the deformation tensor that you apply in your system. Maybe if you're lucky, even activation thresholds. If you want to connect, for example, your microscopic simulation to more mesoscale models, you need some scale, some stress, some activation barrier. And then how these defects they start to interact and lead to emergent phenomena through either elasticity or plasticity. And also, when you have these tools, you can ask, if you have a way how to characterize your glassy system or your viscous liquid, you can also ask what is the effect of the protocol, the effect of the temperature, the effect of mechanical edging, thermal edging, once you have a tool to visualize efficiently your system. And so my tools, they're based on mainly the potential energy landscape. So I will think about like more zero temperature, so I will not even have a thermal activation. But since I'm deforming my system, I can still hop from one minima to the other by applying some stress. And if the stress is large enough, if the deformation is large enough, at some point the system will become unstable and relax to one new minima. And so in terms of landscape picture, you start to increase here gamma is the strain, you start to deform your solid, and at some point there is a critical strain where the system will flow and produce some plasticity. And when you actually look at already at the curvature of the landscape, so what will be the unstable mode that make you flow, if you look in space how it looks like, indeed it's not something which is delocalized everywhere in the system, it's something that is very localized, and it's really particles that will undergo a small shear transformation. So some particle will go out and go in and release some stress. And in the jargon, those modes, they are called quasi-localized modes. So they have a local core and some elastic kernel, which is a bit more long range, So we learn quite a lot of things associated with this quasi-localized mode. And so the idea was wanted to make a quick sum up in one slide of the things that we learn about their population and about their micromechanics. So one thing that we learn is that those modes, they are not only there when the system is unstable at the onset of a plastic instability, but they're actually everywhere in the system. But some mode might be soft and some mode might be very stiff where you will not see any rearrangement. So if you actually look at how they are distributed in frequency, so it's a density of state of my local mode in a glass, you see that indeed the majority will be maybe strong, but you can have anomalous region in the system where you have really a soft mode that extends towards low frequency. And one thing that this community, not only me, but many people in this room learn is that in the low spectrum, we found a peculiar statistic for this mode. It's follow omega to the 4. And what was interesting is that depending on how you make your glass, if you quench it very fast or if you quench it very slowly, so this will be my temperature, high temperature and low temperature in blue, you see that you really have a depletion of soft spot in your system. So the picture of that will be that poorly annealed glasses have a lot of weak soft modes, and a very stable glasses, well annealed, will start to have a depletion of these modes and a depletion of the prefactor of this density of states. And in the point of view of mechanics, we also learn a lot of stuff. So first of all, because if I'm making a map and I'm telling you how is it soft, just in terms of the mode frequency, it doesn't tell you anything about mechanics, because what you would like to know is not only the frequency of the mode, but how is it going to soften or stiffen upon deformation. And what we learn is that actually modes, they have an internal coupling. So for example, if you will already use the method like the local lead stress center around the mode, and you will forget everything. So you're freezing everything and you're just shearing it. So you're not talking to any part of the system. Already at that level, if you will change the orientation of the shear deformation, you will see a different coupling. So internally, they have a coupling with the remote loading. And then there will be other coupling, because when you deform your system, you're in a heterogeneous elastic media. So there will be two types of things that can affect the dynamics of a mode. One is just just elasticity. If I'm starting to shear my system, I don't see any plasticity. There are no dissipation, no actual rearrangement. I just undergo elastic branch. The system will affinely deform, but then to restore mechanical equilibrium, it will respond to that. And we already know that even without dissipation, the displacement field is actually show long-range correlation. So already through elasticity, those soft modes and their dynamics, they will be influenced already at the level of just elasticity and not even dissipation. When you start to see dissipation and a shear transformation, we also learn one thing is that there will be some stress release across the system, and those will be also long range and follow the green function of a glass. What it means in practice, it means that when you have a shear transformation zone, all the modes and the defects around, they will be less affected if they are far away, but then there will be also a symmetry. Some modes will stiffen and some mode will soften in a particular fashion. And the sort of combination between elasticity, plasticity, and the quench disorders that you have in a glass will lead to different response. And this type of depletion, it was not only seen, of course, in methods which are based on the landscape, but also the local yield stress. So if you take a high temperature glass or a glass which is annealed very slowly, you have a depletion of defects. And you also see this in machine learning based method like the softness that Andrea will talk about, and also some purely structural metrics where you see a depletion of unfavored structure. Okay, so one of the things that I wanted to do is to try to make a quantitative, at least in the limit of soft defect, try to make a quantitative connection between my soft mode in my system, my quasi-localized mode, and local yield stress or activation barrier. So one thing that we can do with our method is to ask the following thing. Imagine I have an ensemble of glass, and in each glass I'm going to try to find what is the excitation that if I will push my system along, will move me across a barrier with a high delta. So I can do that by both minimizing the stiffness of the mode and maximizing its symmetry. And so for an ensemble of glass, I can ask what is the softest mode in my system, if you prefer. And one thing that we realize at the quantitative level is that actually stiffness and asymmetry, or frequency, if you prefer, they're actually related in the asymptotic regime. So if you only take the weakest spot in your system, and they are actually linearly related. So tau the asymmetry and omega the frequency. And that was interesting as a quantitative level because we know that the strain distance to an instability, so x, which will be just the critical strain minus the strain R. We know that this distance should scale for small distance, it should be the stiffness square divided by tau. So if you have a relation like this, it gives you a relation between frequency and distance to threshold, local yield stress. And since we know how the frequency scale in this asymptotic regime, that gives us a prediction, for example, of how the local yield stress in a glass should scale. And so this relation between distance and frequency, visually, what does it mean is that if you take a piece of glass and you apply the local yield stress, so everywhere in my system I'm measuring how much stress I need to put to yield in a specific geometry. So white region will be the ones that are very soft, is the one where you will see plastic instability, which are marked in black circle. If you do this mode analysis already in the AISSAI class, so at zero strain, you see that indeed in those regions with small local stress, you will have a soft mode. So that's making a connection between small local stress and soft modes in the system.
So these are the softest modes? Why did you pick up just these 10?
Those ones I pick up to illustrate this. The modes, they are everywhere in the system. The problem is that here I'm showing in the specific direction, so I need to know which one in my system is going to soften along this deformation. So if I will repeat this for a different, there will be other spots, other local stress, and other modes which are relevant for plasticity. And this I will probably, Sylvain tomorrow will talk a bit more about this, but those formalism, it's also linking the height of the activation barrier with the distance to thresholds, which will be a relation which is 4 to the 3. And this sort of make a connection between stress, strain distance to threshold, and activation barrier for viscous dynamics, for example. What I show you right now, what I was able to do is only looking at the asymptotic regime. So I'm only talking about the relation between quasi-localized mode and yield stress for the weakest spot in my system. Ideally, what I would like to do is to be able to get all the micromechanics of the soft modes for even large deformation, not only the 2 first %. That's very difficult. So we have already worked out some of the terms of this dynamics, but we are not there yet. And one step that we did before reaching this point was to try to understand already if I would have pairwise energy, what is the micro nonlinear strain energy expansion associated with this? So what is the strain dynamics of a pairwise energy in my system? And how is it related to quasi-localized mode? So I'm considering a glass, and what I want is that I have a pairwise energy between 2 particles. The energy of the system is just the sum of all the energy, and my system is force balance. And what we recently succeed to work out is that at the level of bonds, we could work out a nonlinear strain energy expansion for a given deformation tensor. So now I don't only know the potential energy, but I know how is it going to change at some orders in strain if I start to deform my system in a given deformation tensor. So you can do this kind of tricks. And so for each coefficient, what you will have to find is you will look at the total deformation. So there will be an affine, a non-affine part. So for example, for the first coefficient, the affine, you might know them, it's just the stress. But there will be also some non-affine response when you want to restore mechanical equilibrium. And so you can do that. And so now for each bond, you know how the energy of locally of 2 particles will change. And so you can, of course, get the coefficients, the nonlinear coefficient at the bond level, but you can also sum of them and just get the microscopic strain energy expansion of your solid. And then try to connect also how those non-affine parts connect with the population of soft modes. So maybe just one slide on the relation between micro and macro. So with this framework, without looking at microscopic, you can already get the microscopic nonlinear coefficient of a strain energy expansion. So you can follow all these coefficients as a function of strain, different preparation protocol, and you can look at on loaded samples. So I shear and I have a state which are at finite stress, and I can also unload my system, for example, at 0 stress, and look at the evolution of that. So that's a lot of information, so I will not go in detail, but for example, one interesting one, for example, is so the first coefficient is just the stress, the second is the shear modulus, and then you have some nonlinear terms. And so for example, with the third coefficient is the one which is the odd power of the strain. So that will give you information about polarization. If you take a glass and you just quench it, this coefficient will be 0 because you didn't do anything to your system, so there is no way that you will deform differently if I shear it positively or negatively. But when you start to shear your system, you will activate plasticities that commensurate with the deformation, which means that you really have a mechanical history in the sense that if you will take your system after a lot of plasticity and unload the stress by just deforming it back a little bit, you will see that now this coefficient is not 0 anymore, it's positive. Which means that if you will take this sample at 0 stress and shear it back, it will fight more in the positive direction than in the negative direction. So that, for example, at the level of macro, those tools allow you to distinguish between a state that experience some plasticity or not. Now at the level of the micro, because we can detect polarized glassy state in some sense. And so now at the level of the microscopic, so now I don't only have the global coefficient, but I really have the coefficient for all the pairs. So I can ask, is there anomalous variation of energy in my system? And indeed, what you see is that the change of energy is not homogeneous, but you will have some regions that will show a large variation of energy, which will help you to predict where there are going to be large deformation. And when you start to take higher nonlinear term, you can pick up what are the soft spots in your system that couple the best to the imposed deformation that you use as an entry. So that gives you a map for a particular deformation. So you could repeat this thing for other type of deformation. So that's really a tensorial map. And you can do this in 2D, but you can also easily do it in 3D. And the advantage of the framework is that you only need to solve linear equations. You don't have to fully diagonalize the Hessian matrix of your system. So you can actually look at this in real system in 3D. Most of the methods which are based typically on the landscape, you need to diagonalize your Hessian to get all the modes. And diagonalizing an Hessian when you have, I don't know, 250,000 of particles, it's very tricky. So now a quantitative connection, because you see that you have a clear soft spot, so that already gives you an idea that there might be some soft mode underlying that couple ways with this deformation. And we can actually make a formal analogy where we know that from the structure of this coefficient, for example, I take the first one, if the density of states will scale as omega to the 4, we will expect that there will be a large variation of bonds that have a coefficient that decay as to the power 7. So those anomalous tails, they are like telling you about defect in your system, and then you can ask, how does this tail change if I change something in my system? So here I'm changing the parent temperature, so it's the temperature at which I equilibrate my liquid using a swap Monte Carlo, and you see a depletion of this tail. And graphically, it's really like the same picture that I showed you at the beginning is a depletion of the number of soft modes that you have in your system. All right. So then I talked to you about plastic polarization. So in some sense, you have soft modes that couple well with a given deformation, I showed you, but it would be nice also to know, are they coupling in this deformation in the positive direction or negative direction, for example? So imagine positive simple shear along, I don't know, x direction and negative simple shear. And some people try to already have such information, so to have a map of soft defect in the glass, but to color them according not only to the deformation, but also the direction of the deformation. And they were able, for some of the soft spots, to detect that this soft spot is going to couple well in simple shear in this direction, and in the red one, it will only couple in the negative direction. So I wanted to do a bit the same thing with my tools. And the idea here is to combine coefficient of the strain energy expansion in a sense that if you approach an instability, you know that some of the bonds are going to extend and compress. So at the linear and quadratic level, you should expect that they have the same sign because they will undergo a deformation. And so you can use the product to distinguish which one are going to be stabilized in one particular direction. And if you do that, so it's the same type of information that I show you, but now this time I make a color according to the sign of the product. You can distinguish soft spots that will couple to a positive simple shear and soft spots that couple to a negative simple shear. So you really get a map where you can predict this for a given deformation and on top know the direction of the loading. So you can make, for example, a map which looks like this, where you have the activation and deactivation of the defect depending on the geometry of the loading. So I wanted to a bit compare, like if you start to have a polarization, you know what is the optimal angle for which a soft spot will yield. Imagine in 2D it would just be one angle, the angle of the shear deformation. So I wanted to try to compare like this method, the quasi-localized mode and the method of Silva, the local yield stress on the same footage. So I will just show one example. So I'm taking the same glass, and so I'm taking this soft spot which appear to be blue. So good coupling with positive simple shear. And now I'm going at this soft spot, I'm going to find a mode, and I will compare the micromechanics of the mode to the polarization of this indicator. So I don't have the complete, as I say, micromechanics of nonlinear modes, but I can at least work one thing is the first coefficient, which means how the energy of the mode will change with the strain. So I can already tell you if I have a mode at small strain, is it going to stiffen or is it going to soften? And it's what you see in red. So it's normalized between the softest, which will be negative, and positive stiffening. And what you see if you compare it to the product is that region with the blue product, they correspond to region where the mode will soften the most, so where the change of energy will go down. And so you can distinguish two poles, which will be like the most favored direction and the least favored direction. And those, they actually follow some symmetry. So this is one strain derivative, so it will follow the symmetry of the stress. And here there will be a combination between symmetry of stress and symmetry of elastic constant. And then you can take the same patch here and now put a cavity around and do the local yield stress. And so I can now take my blob, freeze my matrix, and then I shear it in, for example, the green and orange direction. And this is what you will see. In the least favor, you can undergo large deformation before to yield. And in the most favor, you will directly yield for a small deformation. And you can do this for any sheared angle. And indeed, you see for this case, for these guys that are that couple well with a positive simple shear, you have a basin of small local yield stress. What is absent in this picture is that the local yield stress not only give you maybe the most favored, but it also will give you indication of our other yield plane. So you imagine that if you take packing like this, there are not only one direction where you will be able to flow. There are actually many angles where the system will be able to undergo a transformation. All right. How long do I have?
It's almost time.
Okay. So just one application of that. So one thing that we looked before was one limit was to ask, can we look at zero activation and and zero strain rate, so in athermal quasi-static yielding, and one limit will be the small disorders that you can achieve with swap Monte Carlo. In this limit, you can it's interesting because you can basically undergo all the way to yielding. You can go all the way to yielding without plasticity and then yield and form, for example, strain localization. And so one question in terms of prediction was, can you predict where the shear bend will occur from the AISSAI structure? Some people have already looked at this, for example, for the local yield stress. And this is an ensemble average over many realizations, but they look at the local yield stress where they center the distribution of the system to the direction of the shear bend. So 0 is where you will have the shear bend. So of course, close to the shear bend, you will have small local yield stress, but they saw that in the AISSAI quench, there was some sign of polarization where in the system there will be a hint of where you will nucleate strain localization. But this was average over many samples. I wanted to see with my tools, can I do this at the level of one system? So here I'm showing you the strain energy expansion per particle at zero strain, and then I take several terms from linear to nonlinear terms. And indeed, you see that even if it's noisy, you can see some of the site where you will be able to nucleate a shear bend. So with this, I will conclude. And so I show you some different structural indicators which are tensorial in the context of plasticity. I show you some quantitative connection between bond strain energy expansion, quasi-localized mode, and local yield stress. And one of the things that we are going forward is to go beyond the asymptotic regime, but trying to, from those tools, to work out the nonlinear micromechanics of soft modes to then start to get large activation thresholds. So is that thank you.
Time for questions?
I have a question about maybe the first part. I think I just didn't follow at some point. I just didn't follow maybe, but you talked about the local yield stress and an activation barrier. How do you define the energy to yielding? How is it different from the local yield stress? Is how much stress you need to apply, and for this corresponds an energy? I missed a point about the activation barrier thing.
Okay. So what we
and how they're different in your scaling of 3 to the 4th,
Yeah.
or I forgot the number, but
so what we know is in the small barrier limit, we know that the barrier is going to be the, just for a cubic thing, you will know that it will be the the second coefficient and the third one. That gives you the barrier. Now we know that tau is related to kappa linearly, and we know
the interpretation of the barrier is the energy.
is the height of the barrier in the landscape.
What you do is you take the thing and you shear it until it hits.
So here it's just a formal formal analogy. Like when you do this, you do they did different things. They measure the local distress, and then they measure independently the activation barrier, like from relaxation time. You will have a talk tomorrow that tells you all of the detail. Me, I know if I have a barrier in the close to an instability, I know what is the asymptotic. I know the relation between frequency and symmetry, and I know the distribution of frequency. That gives me a connection between distance to instability and frequency. And for a cubic potential, when you're very close and you can approximate your landscape by this cubic displacement along this mode, you know what is the height of the barrier for this potential, and that's it, exactly.
Do you actually understand these scalings that come out?
Not much. So we understand so we don't understand fully why this should be linear with the frequency. We know why it should be bounded from above, because all the modes that for example, here are above this line, they will mean that their second inherent state, when we also add the closure of the double well, they will have a higher energy than the minima. And when Boltzmann will just kill this because he will let you go to always the lowest minima. So we know why we don't go above here, but we don't know why it's bounded from below. So yeah.
Other questions? So I have a question actually, or a clarification. I didn't understand. So when you say macro, so the macro properties are the nonlinear coefficient of the, let's say, macroscopic nonlinear coefficient?
Yeah, but they are the one with both the affine and non-affine response.
And then, okay, so I thought that it was, argued by Prokach and others that they don't exist after the second order, no? Or I'm wrong, or maybe I'm not understanding.
No, they do exist.
Yeah, of course they exist in a finite system, but then in the thermodynamic limit they do not. This was their claim.
No, I think it's more. I think he's more thinking in the claim of saying that since in the thermodynamic limit plasticity goes to 0, there is no. But you can still take any expansion at 0 strain and do the calculation because the energy is just analytic. You don't know anything about plasticity, but you can still you can define them, of course.
Yes, but then I think they have a non-trivial dependence by the system side. So that's what their point, I think. So meaning that there doesn't exist a limit when n go to infinity of nonlinear coefficient.
Yeah, they will take over because they will be asymptotic, and then it will change as a function of n. Yeah, you're right. Yeah, I'm not sure actually.
Okay, well maybe we can discuss just later. Yeah, you sum over the local.
You sum the local stuff to get the global stuff?
Yeah, but when you sum, they're different things because you have different terms which are at the bond level and are not at the microscopic level. Some cancel just to make mechanical equilibrium. But in any case, his point is to say that I think his point was to say that some are asymptotic, and so that's also true for the shear modulus. So no, that's actually not. The argument for plasticity.
The argument was just that the shear modulus exists in the thermodynamic limit. It goes to a finite value, and I don't know the gamma when the one with 4 gamma it doesn't. It diverges.
No, it doesn't. No, I don't think it's correct.
Okay.
No.
Well.
No.
You should discuss
in terms
with
of
Itamar,
structure, there is nothing in terms of structure that will. No.
Okay, discuss with Itamar then.
I see him. I see him in a week actually.
Good.
Sure
all right.
Like
So
discuss,
thank you very much.
Celui-là c'est le mien, mais je te le laisse si t'as pas envie de changer. Non, c'est bon. Ok, ça roule. Par contre, ouais, que je parte pas avec. Je mets ça dans la poche et puis ça détaché.
All right, so we start with the second talk of the afternoon session with Camille Scalliet from Cambridge. So thank you, Camille.
Thanks. So good afternoon, everyone, and thanks to the organizers for giving me the opportunity to present this work. So this talk is actually about the dynamics, and its aim is to inform you on the physics that we observe at very low temperature in glasses, so that maybe machine learning techniques can be deployed there. Okay. So I will actually speed up the slowdown description that Olivier described earlier today. But just to mention here what sort of regime and what sort of physics I'm discussing about. So here in this complicated phase diagram with volume and temperature, the specific regime where I'm going to focus is the supercooled liquid regime here. So you take a liquid and you cool it rapidly enough to avoid the crystal. And what we have been discussing about is the fact that the dynamics slows down dramatically, and we want to understand why this happens. So this is equilibrium physics. We're not yet in the glass, which happens at glass transition temperature Tg, which is determined empirically as a relation between the microscopic time for the liquid to flow and the time that you have to observe the liquid. So I want to discuss this region here, and I want to go back to experiments. So here I will be talking mostly about experiments on atomic and molecular glasses, which have quite specific timescales. So here in experiments, what you have is the relaxation time in logarithmic scale as a function of the inverse temperature. So low temperatures are on the right here. And what you can observe in many molecules or atomic liquids is this dramatic increase. And you have this huge slowdown by more than 12 decades. So you can observe this. You have these huge relaxation times. But the real problem that we have to understand this is that you have very little spatial or microscopic understanding. You can just measure average bulk properties, but you don't really understand why the dynamics is so slow. So really, the question here that we want to address is to understand what's the origin at the microscopic scale of these huge relaxation times. So we want to address that with computer simulations. The reason is because in computers, you directly simulate the trajectory, so you have access to all the microscopic information. So this allows you to get more information and more insights as to what's going on. The problem is that this happens to, there is an expense to this thing. Computer simulations were much slower than actually nature and real experiments. So this has been a huge limitation for most studies up to now. So I want to go through some discussion about the timescales here. So in a simulation in around 2 weeks, which is a reasonable timescale, you can simulate up to 10 to the 7 tau 0. So tau 0 here is the relaxation time at which you start to see this glassy slowdown. So this is the timescale that you have. So in this plot here, this corresponds to this limit here, so 10 to the 7 in these rescaled units. And if you want to do in this simulation, if you want to study the supercooled liquid, this corresponds to an equilibrium state. So you need to ensure that your liquid is actually in equilibrium, and that requires to run the simulation over many relaxation times, because as Olivier described, this relaxation time corresponds to, let's say, half of the particles that have relaxed, but you really want to have sampled many equilibrium configurations. So this sets, let's say, hand-wavingly a limitation on the relaxation time that you can study in equilibrium with molecular dynamics or Monte Carlo simulations. And you lose basically 2 decades for this equilibration. So this means that using molecular dynamics, you can investigate liquids with the relaxation time up to around 10 to the 5, which is really far away from the experimental conditions. So here TC, I'm going to discuss this later, which corresponds to the mode coupling crossover also, for those who are familiar, corresponds to the computer glass transition. And this is really different from the experimental glass transition, which corresponds to the point where if you extrapolate, you would reach 12 decades of slowdown. So very recently, there was this huge breakthrough, I would say, in these computer studies, which correspond to the optimization of the particle swap algorithm. So you probably have heard about it. It was developed in this paper by Ninarello, Berti, and Coslovich in 2017. And we implemented this in LAMS to be able to share it with other users. So the goal here is really to bypass this long equilibration, which is really limiting the timescales that we can study. So the major consequence of this particle swap algorithm is the following. If you investigate the liquids at a low temperature, so let's say here on the right, you see that the real physical dynamics is actually too long to be able to simulate. But now if you add just a small change, these particle swap moves, what you have is that the dynamics is increasing, is dramatically sped up, and you can actually, in this swap dynamics, measure the relaxation time, which means that you're still in this region here where you can do equilibrium simulations. So the consequence is that you have access to equilibrium configurations at temperatures that are down to the glass transition and actually even below, even though the physical dynamics is really too slow. So the main point that I want to discuss here is the fact that in this regime here, between the computer glass transition and the experimental glass transition, you have a completely new territory for both computer studies and also machine learning. And I want to discuss what we have here. And most importantly, this is also the temperature regime where theories make some useful predictions, for example, by comparing the thermodynamic and the dynamic sort of descriptions. So this is what we've done in collaboration with Benjamin Ghiselin and Ludovic Berthier. So we use particle swap as a tool to generate equilibrium configurations. And then we take these as starting points for standard equilibrium molecular dynamics simulations, as everyone has done before. And we run the dynamics for as long as we can. So what I mean by as long as we can is really long simulations using many CPUs and also using quite long simulations time. I will show you, for example, 2 months simulation. So we're able to reach some really long simulations time, 10 to the 8, which is even a bit beyond the limit that I put before. And here the main point that I want to make is that even if the relaxation time is much longer than the simulation time, you can still run and observe the beginning of the relaxation, and this is actually really informative on the physics that's happening there. So first I want to discuss the average correlation function. So these have been computed over and over in many different systems in the past decades. So this corresponds, for example, to the self-intermediate scattering function. So this correlation function is shown here. So it goes from 1 to 0 at long times. Here I'm showing the results in logarithmic scale. And this plot was actually shown this morning. The main point that I want to make here is that all these curves here are measured in the regime that was not available before. So here, this blue curve here corresponds to the mode coupling crossover or the computer glass transition. And this corresponds to the lowest temperature that was available before. And now, starting with these equilibrium samples, we can run the dynamics down to temperatures that correspond to the experimental glass transition. So if you look at this plot, you think, well, this is rather featureless because you mainly just measure a plateau. You wasted your simulation resources. But actually, if you go to another type of description that is used mostly by experimentalists, they compute what's called a dynamic susceptibility. So now this is in terms of frequency ranges, with here short times and here long times. What you transform this data in these spectrum here that basically tells you the amplitude is correlated to the amount of particles that are moving at a given time scale or frequency scale. All right. So what you see here is that going to lower temperatures and going especially to the experimental glass transition, what you have here is a signal. We actually fit it well by a power law. And what this is telling you is that while here you have the feeling that nothing is happening at all, what you have is a signal. It's low in amplitude, so it means that a few particles are moving. But it still means that what you have in the system is a broad distribution of timescales or frequencies over which particles are moving. So this typical picture of particles are just stuck here and vibrating and then eventually going to relax at tau alpha is wrong. And what you have are dynamical processes over all times and all frequencies. I will go back to that a bit later.
So is the power law the same throughout temperatures?
It evolves a bit with the temperature. So the thing is you can measure it only in a short temperature window. It evolves a bit, but it seems to be quite constant. And this is 3 dimensions, and in 2 dimensions, the value is a bit different. I can discuss about this. But now we have computer simulation, so we can go beyond what experiments can do, so we can actually have microscopic insights into what's happening. So here I take one of the systems that's at the lowest temperature at which we're able to see 2 alpha, and this requires still a 2-month simulation. So in terms of timescales, we're roughly halfway between the mode coupling and the experimental glass transition, so really deep into supercooled liquid. And this is the initial structure, so the particles correspond to the size of the particle, they're polydisperse, and I think that no one here by the eye could sort of predict or tell what's going on. I'm going to show you the movie of the dynamics. So here, this is the same configuration. I'm going to simulate this over extremely long times that are actually 5, 6 tau alpha in this case. And I'm going to show the dynamics as we go through the simulation in terms of this indicator here. So this indicates the fraction of initial neighbors in the structure that the particle has lost. So it's just telling you if the particle has relaxed or not. So blue particles correspond to the initial structure, and red correspond to a new structure. So if I show you the movie, you see some quite striking spatial temporal pattern here for the dynamics. And you can see that it's, well, maybe you can actually see that even in these red regions, you still have a lot of rearrangements. And eventually, you have some regions that have not relaxed even after several relaxation times. So here, this is a summary of what we observe, going from short times to longer times here. So 2 alpha corresponds roughly to this snapshot here. So what we have and what I will describe and quantify in the next slides is the following. So what we see is that very early, much earlier than 2 alpha, we do have particles that have relaxed, these corresponding to these red clusters here in which the particles have rearranged and lost their neighbors, hence appear in red. So we have these clusters here that appear, and then as time increases, what you see is that these clusters increase in size here, they grow, and eventually, at longer times, they start to merge, and the dynamics proceeds by the growth of these existing regions. So let's concentrate first on the early times, which give rise to this power law in the spectra. So I want to explain a bit more what's happening here, and especially quantify what we observe there. So here at short times, what you have are regions that start to pop up in the configuration where relaxation starts. And what we see is that this doesn't happen on a fixed time scale. We see that it's a continuous process, and we want to quantify it a bit more. So here I have a few clusters that's observed at very low temperature. And what we do here is we measure the time, tau1 for this first cluster at which it first appeared, and then for each of these clusters we record the time at which they appeared. And then we construct this distribution here. So this is the distribution of this time, the apparition for these mobile clusters as a function of the time, and we rescale everything by tau alpha because this is increasing dramatically as a function of temperature. So this allows the comparison between high temperature and low temperature. So here in this curve, corresponding to the mode coupling crossover, what you have is already a broad distribution. So you see that already 4 decades before the alpha relaxation time, you have clusters that start to appear. And this is a continuous process. Eventually, at longer times, they merge, so this distribution goes down. Now, as the temperature decreases, what you see is that this distribution expands to lower and lower times, and eventually it covers many decades in times, and it follows here, as you can see, a power law with a similar exponent that I discussed before. So the main aspect here is that the relaxation starts actually at the very start of the simulation. You have here 12 decades before the relaxation time, some mobile particles that appear. This is a continuous process indicating that there is a really broad distribution of timescales for the apparition of these clusters, not just one. So maybe an important point really that I want to make here is that there is no binary distinction between fast and slow particles. There's a continuous and extremely broad, over several decades, distribution of timescales. Now, I want to show you also what's happening maybe at higher temperature, which is what people are more used to. So here I discussed the very low temperatures that correspond to temperatures close to the experimental glass transition, so really completely new physics that we're observing. But if we go to slightly higher temperatures, here I'm showing typical snapshots of the system when the decorrelation is around the same. So let's say 2% of the particles have moved. What you see here, actually not so well, but that's probably the main point. At the onset of the glassy dynamics, what you have are particles that are a bit whitish, meaning that they lost maybe one neighbor. So the motion is really highly collective and quite soft. Close to the mode coupling crossover, what you have is a picture that's maybe a bit clearer, where you start to have some more compact zone, but still you see that in these regions there's no very, it's a quite subtle move still. I will show you actually in the next slide. And you really need to go to extremely low temperatures to see these very well compact regions that start to appear. So going a bit on this and these discussions that we've been having about either collective moves corresponding to soft modes versus activation events, that's a sort of long-standing debate in the community. What I show here are, so exactly for these two snapshots here, I'm showing actually the displacement fields of the particles so that you can have a better feeling of what's going on. So here at short times, I show the displacement field of the particles, and here on the right, I'm showing this inset as a zoom here. So what you have are these particles that were appearing a bit in white, corresponding to just one or two neighbors lost, correspond to these very collective soft mode-like displacements that have been investigated a lot in the past. You see that the particles move collectively. While at much lower temperature in these mobile regions here, what you have are much more complicated relaxation events. I think you would agree with me that this corresponds to highly complicated moves, and actually to get to this point here, the system had many relaxation events that give rise to this huge displacement. So particles here move 5 diameters apart, but this happened by the accumulation of many relaxation events, while here there may be 1 or 2. So this is a point that I want to describe a bit afterwards. So now moving from short times to longer times, I showed you in the movie that there is a clear structure in space and in time as how the dynamics proceeds, starting from these initial clusters. So here I'm showing the same data, so the same configuration, but now I'm plotting the particles with a color that codes for the time at which they lost half of the neighbor or their local relaxation time, so for each particle. So it goes from red at very early times to dark blue, and this corresponds to 9 decades in time later, so a really huge separation in time scales. So the clusters that I discussed correspond to these red regions. Here you see that they're really rare and a priori far apart initially. And then what you see is that in this structure here, you can read this color code from red to blue. So for example, here you have some particles that move early, and then you have a continuous color code going to dark blues. And what that means is the fact that the particles here moved very early in time, so they correspond to these colors, helped the relaxation of the neighboring region at later time. And this is the dynamic facilitation idea that Olivier described. So the fact that you need to relax in one region to be able to help the relaxation in neighboring regions. So here, something that is actually striking. This is equilibrium dynamics. I insisted on this aspect that is really important. And I'm showing you the dynamics that's going on in logarithmic scale in space. So you should be, I don't know, a bit maybe surprised by this fact, because this is equilibrium. So in each time frame, you should have the same amount of relaxation events. This is time translational invariant. So what that means, the fact that you see this log scale spread means that you have relaxation events that are actually taking place in these locations over and over in time in order to be able to eventually relax the neighboring region. And this is something that I will quantify just afterwards. So here again, I want to show you and give you an idea of what you get by going to much lower temperatures. At the onset, you don't see a very clear pattern, and then eventually at the lowest temperature where we can see 2 alpha, we see a very clear distinction between the regions that have relaxed in red and those that haven't relaxed. So here in this slide here, what I want to show you is that at these low temperatures, at these low temperatures, you see that you have very clear regions that have relaxed in red, and that here you can actually directly measure their size. I think that by the eye you can see this size. Here, if I ask you what is the typical size, you would say, well, maybe 1 particle or 2. So here we were interested in quantifying this idea of dynamic facilitation, the fact that the dynamic spreads in space over time, and to try and see if it's diffusive or if it's subdiffusive, or try to really quantify this sort of dynamics. So at low temperature, we have these compact regions, and I mean, this is already, I want to mention that this is not trivial. You really need to go to low temperatures to have this. And this allows to directly quantify their length. So with this chord length distribution, so sorry, I don't want to go too much into the detail, but the idea is that now we can directly measure their length instead of doing some 4-point correlation or things like that. We directly have a length here. And we can measure this average length for the clusters as a function of time. So here I'm showing the data as a function of different temperatures. So from high temperature here, corresponding to the mode coupling crossover, to much lower temperatures corresponding to TG. And again, this is rescaled by the alpha relaxation time so that we can compare different temperatures. So what you can see here, sorry, this is not COVID, but in Cambridge there is a cough that's going on through the whole university. Okay. So what you have is really a qualitative change in the growth of the average. No, it's not going to go. Sorry. You have a qualitative change between the mode coupling crossover and TG here. So at high temperature, the clusters don't really have time to form and grow. They directly merge because there are so many clusters. While at lower temperature, what you have are these very well-defined regions that have time to grow and increase in time. And we can actually fit their growth here by a power law. So this is actually a way to directly quantify and characterize this slow growth of the domains. So we have this, this relation here in which we introduce a dynamic exponent which relates time and length of these dynamic heterogeneities. And the fact that we can measure this is highly informative, because what you see here is that this dynamic exponent is huge. It's 6. So this means that the dynamics is highly subdiffusive. So these regions start to pop up, and then they grow, and their growth is extremely slow, and we can directly quantify it. So, so in these data, what you can see is that this exponent changes with temperature, and this is being measured independently by Cecilia Herrero in Montpellier. And what we have is really that the growth is slower and slower at low temperature. So now in the simulations, what we see, what I tried to give you a flavor of, is that in these mobile regions, what you have is really an accumulation of many, many, many relaxation events. So we introduced a new way to quantify this idea that the dynamics repeats itself and accumulates at one location. So here we look at the particles that are mobile between 0 and delta t, and then we look at the next time interval, and we look at the fraction of particles that are mobile in the two regions. And this indicates basically how much the dynamics accumulates in one region as a function of this time interval here. This is a measure of how repeatable or accumulative the dynamics is. And we do this measurement as a function of the time interval delta t, again scaled as a function of tau alpha, for many temperatures, from high temperatures to low temperatures closer to TG. And what you should see here is that the timescale on which the dynamic repeats itself the most is actually the alpha relaxation time, so when half of the particles have relaxed. But most importantly, what I want to really stress here is that at low temperatures close to the experimental glass transition, also at extremely short time scale, the dynamics is highly repetitive. So the fact that this value here is high even at extremely short time scales compared to tau alpha. Yes?
How many of these are reversing themselves?
Sorry?
How many of these events are reversing themselves?
So we haven't quantified that. Some of them are. Maybe I can expand a bit more. Okay, so what we have here is this accumulation, and really our hypothesis is that this is driving this very slow growth. You need to accumulate many events eventually for the timescale to increase. So the conclusion of this work and the open theoretical questions are the following. As we go to lower and lower temperatures, going to the experimental glass transition in simulations, we observe two things. The first is that there is a distribution for the apparition of these mobile regions that we can measure directly. We see that they appear on timescales that are power law distributed, so there's a huge distribution of timescale for these mobile clusters to appear. And then at later time, each region grows in time, and this growth itself is increasingly slow and very, very slow. And we characterize this by a power law and probably even a logarithmic growth. So we have two effects basically in the slow dynamics, and both change with temperature, so both the apparition of the clusters and their growth. So there are mainly two reasons for which the dynamics can slow down. First one is the distribution here gets increasingly broad, and this is in part what we observe. And the second thing is that once these clusters appear, they grow increasingly slowly. So the question I would say now is maybe a bit clearer in terms of, let's say, it directs the effort on these two questions in terms of characterizing the dynamics. The question I think now is to understand if there is one which is dominating the growth or not. And in this framework here, one question is, these domains here that start to appear, are they correlated with the static or not? So this is an open question. And second, is this also related to some statics or not? So here in these new simulations, what we're able to do is to also inform and provide new data in this new regime. So here I'm showing two length scales. So the first one is the average length at the alpha relaxation time, so when half of the particles have relaxed. And the second one is a thermodynamic length that can be measured. It's the point to set length scale, and Olivier presented it in the beginning. So I think that the data that he showed correspond to this regime here, so at temperatures that are higher than the mode coupling crossover. And there was a question, he said they decouple, but there was an open question, maybe at lower temperatures, the thermodynamic length scale increases and catches up with the dynamic one or not. So here we have new data in this regime, and what we see is that actually the dynamic length scale increases, the thermodynamic one also, but they appear to do so with different scalings. And so maybe the difference between both here is actually related to this idea of dynamic facilitation. This is in 2D also, so there is completely open question as to how the 3D works. So just to conclude, for the people in the room that are interested in machine learning, I hope that I showed that there is really new physics to be seen, to be characterized, but I think that it also opens a completely new territory for machine learning studies at lower temperatures. So for example, the current machine learning studies are at temperatures higher than this computer glass transition here, and you see that the dynamics actually starts a bit everywhere, and maybe it propagates, but it's not extremely clear. But at low temperatures, what you have here are a few regions that start the dynamics, and everything proceeds from these regions, thanks to this facilitation effect. And it's, while these regions can be encoded in the initial structure, it's not clear at all to me that everything that follows and this facilitation is also encoded in the structure. So I think that there are even more fundamental questions as to the predictability of the dynamics close to TG, if everything is encoded in the initial structure or not. And I think another challenge is the fact that the dynamics is extremely slow, and this is what we're studying here. So I was able to do one simulation of this 10,000 particle system for 2 months. But now if you need to get a huge amount of statistics to train your machine, maybe this is going to be not so efficient. So I think this is going to be a challenge. Maybe the strategies that worked here will need to be maybe changed, or learning from the successes and failures here, we can maybe study this more efficiently. And I think that in this regime, machine learning techniques that actually help the molecular dynamic simulation is going to be something extremely useful. So I want to conclude. Thank you for your attention. Thank my collaborators, Ludovic and Benjamin Ghiselin. And these are the 2 papers I've been discussing. Thanks.
Thank you. Yeah.
Camille, if you go back to the second to last slide where you had the L, yeah. So if you show the average L as a function of a fixed fraction of tau alpha, then as a function of time, will you eventually see that it converges at short times to the thermodynamic length? Because that would mean something different if it happened.
Sorry, can you, so this is the length?
This is done at the tau alpha,
yes,
right?
Yes.
L. If you do it at fixed fraction of tau alpha,
Yes.
like 1/10, 100 and so on, would it slowly converge towards a thermodynamic length? Because
That's
if this is the case,
yes,
it
sure.
means that the point to set length characterizes these
Yes.
small objects that start to relax, and then the rest is facilitation.
Yes, sure.
So if you can prove it, I think it's a strong point.
I couldn't say that I prove it. Actually, I removed the, sorry. On this slide here and in the paper here, what you have here is a small circle that indicates the size of the point to send cavity. Okay, so this is not proving anything. It's just informing as to whether this is valid or not. I think this is a good question, and I mean this is directly my first. I don't have the answer. That's the short.
But it's easy to do, no? Because
yeah, but then I think that if you have the point to set length scale and you can measure the size of, let's say, the first relaxation event, and it correlates well, I think that there's still the question as to whether this is, I don't know, just a coincidence, or whether the regions that start to grow are actually really the ones that, if you do, I don't know, a small cavity, are the ones that are
just
the least stable.
Statistics and
Yeah.
the average at fixed fraction of tau alpha to see whether this plot converges to the I think
Yeah. I mean, yes, definitely we can try. Sure. I mean, we have the data at least. Yes. Yes.
You tried to look at any of the structural indicators?
Sorry. So yeah. So maybe Olivier, you repeat the question for the others.
But I
No. Okay, sorry. The question, for everyone, the question is, did I look at the structural indicators? And the answer is no. So this is really the first study where we studied a few things. We tried to characterize with new tools the dynamics that we're seeing. But I think that there's, a whole territory of, reproducing all the studies that have been done before, looking at softness, looking at local yield stress. I like everything. I don't know. I haven't done it myself, but maybe someone will do it. Yeah.
Yeah, so can you come back on one of these nice pictures?
Which one?
Well, maybe this one. Okay. No, maybe, yeah.
It's
So
not so nice.
here, what you show is how much the particles have moved, I guess, on a certain amount of time, right? There is a delta t that you choose.
Sure.
If you take it twice, as we saw in the next slide, then 2 of these clusters overlap. And so if you had taken this twice delta t, you would have had from the very beginning a larger cluster. And you could have done this for 3 delta t or 4 delta t. And so you see my question. Or very much smaller delta t. And then this concept of compact cluster at the beginning, maybe it would be just 1 or 2 particles. Or is there a strict minimal cluster size? And if you go to smaller delta t, you never see anything.
Yes.
So how did you choose this delta t? I mean, I know it's a bit of methodology, but it's quite important at that point.
This delta t here?
Yes,
So
for instance, yes.
So let's say the reason why we investigated all delta t's is specifically not to decide on a specific delta t, because as you say, everything changes here. It's long enough such that we actually measure something. All the So for example, at these high temperatures, at super low delta-T's, you don't see anything because you don't catch any relaxation events. So now I think this is another area where work needs to be done. There's all this question of identifying the elementary excitations with the facilitation framework. And I know Paddy Royal and Lefker have been doing some works. So just really trying to catch individual relaxation events. I can tell you from just qualitatively what I see is that when something happens at really low temperature, it's really a collective and, it has a minimal size that I haven't characterized, but there is a size that increases there. And just qualitatively, the picture changes really a lot between, you have these huge things, but they don't do much to the structure, and here you have these small, compact, and highly complicated events that are going on. But this again needs to be done in a sense. And maybe your answer will sort of clarify what Daniele was asking. Is the individual rearrangement correlating with the static or not?
Yeah, and if we imagine that you would have enough statistics to extract the distribution of the size of this cluster, how this distribution of size would evolve when you go down in temperature?
Yeah.
Do you have, are the elementary excitations, the very first one, larger because things are more correlated? Even from the you see, because we did actually this kind of study in the grain case, and there when increasing the packing fraction, we could notice that when we were going to higher packing fraction, so I don't know exactly, given from the picture in terms of compactness and the cluster, etc., even if I don't understand why, in this vibrated grain system, we are in the regime where it's not anymore soft stuff, it's more the kind of clusters that you see. But then when we were increasing further the packing fraction, these initial clusters were getting larger, and so to relax the same fraction of the system, you needed actually less facilitated event because you already had done a lot with the very first excitation. So although facilitation was still the dominant dynamics that would lead to the total relaxation of the system, a larger fraction of the system was already relaxed from the very first events.
Okay, so maybe we need to discuss more into details about that. I'm not sure. So the picture that I showed earlier from your work and our work, I'm not sure exactly how they coincide in the sense that you seem to say that a large thing flips and then there's an avalanche. I think the avalanches that we see are on much larger length scale, and we don't really see them, but I think we need to discuss more into detail about that. But all these are, open questions. Maybe it's time to.
No, there is
have a
time
break.
for discussions.
Yes.
How different is that chord length from the usual C4, from the correlations?
So the question is how is this different from the usual Chi4 correlation? My answer is it should not be different. So it's really meant to characterize the same thing. Maybe one advantage is that it's probably easier to, let's say, more visual. You can see it more visually here than these 4-point correlation, which is sort of indirect way to probe them. The second, I would say, advantage of this is that the 4-point measurement actually changes as a function of the ensemble, either NVT, NPT, NVE. It suffers from ensemble. Changing the ensemble affects the measurement. Here, this is really a length of something you can see, so it shouldn't suffer from these. So I think the reason why people did this 4-point correlation function is precisely because at the temperatures where simulations were done, you didn't have this clear distinction where you can actually say, well, this is my relaxed cluster, it has well-defined boundaries, and I can give it a size. Here, maybe you can, but I don't know, the boundaries are not so sharp, so you need to do this 4-point correlation. Here, it's even worse. I don't know even how to define a cluster. But it's the same information. Yeah.
Follow up on this question quickly. So can you go back to the plot where you have the L?
Yeah.
So there seems to be a fixed point in this graph.
Here?
Can you repeat the question, please?
Sorry. Here, there seems to
There
be.
seems to be a fixed point there in the graph around tau alpha,
Here.
right?
Yes.
Well,
Can I?
what does it mean?
Okay.
And if it really exists, does it mean that there is sort of a non-monotonic behavior as a function of temperature? on the correlation length.
So not
Around that time. I mean, if you go
Okay.
slightly above the time scale, you will get a non-monotonic correlation. Or
So actually, okay, okay. So this is what Daniel is asking about is here. There's the points sort of cross at a time that seems to be tau alpha, and the question is what will happen maybe here. So I wouldn't say non-monotonic. This is going to increase. Actually, something that is important here. This at tau alpha, the value of the length here is directly it's chi4. It's the length scale of the dynamical heterogeneity at tau alpha. If I show you this in linear, this is log scale, but we have been discussing forever that the length scale are actually changing by a factor 2. If I show you this in linear scale, it's going to have the typical behavior that Olivier showed that Andrea is asking about. So actually, it increases as temperature decreases.
yeah, but I have the feeling that it may decrease if you go slow, if you lower the temperature further.
Ah,
I have that feeling.
good question. I don't know. I haven't measured it. I don't think that it
This
should.
has been seen a little bit, you know,
Okay.
from simulations by Jegosh and Elijah and so on. So I hint that something is non-monotonic, and also by the weekend value. Something
Yeah, but
that is
it's been seen in the regime that there's
yeah, that's why I attempt.
Yeah,
there we would see some
I don't. I would. Okay, I don't know. I would say that it shouldn't go down, but I don't know. Then this is set by the competition of how many nucleus you have for mobility and how fast they increase, and this gives you the recipe to build the picture at tau alpha, and then you will have a size. I don't see why it should decrease, but I mean, open question. Okay, more open questions then.
Could we look one more time at this beautiful slide with the map of the displacements? Yeah, just before with the map of the displacements across the three. Yeah, this one. Okay. I'm trying to make a connection to to Laura's talk this morning, and you've called for applications of machine learning. So if I parse this correctly, if I look at the middle graph, then we use Laura's method. Then it would appear to me that this autoencoder should produce a map that looks very similar to the middle map. Is that correct, Laura? Do you agree? It's but it's not the propensity, but it's something that is presumably closely related. So it's one of the first questions then, if one were to apply the autoencoder method to the figure on the right, would we then expect that the autoencoder reproduces that figure on the right, or is there different physics going on? Is that the first set of questions that appear? Or?
Yeah, these are open questions. So I think I'm not sure whether the machine learning can predict precisely. So this is one run first. Machine learning has to have many runs and sort of averaging and having propensity. So this is one first difference. So actually okay, so you need this, you need propensity, and then you need to be able to use the machine learning tools. One first question is, actually, if I do the propensity map at this temperature, is it also sharper than here or not? This is open question. And then if, I don't know if that would work. I think that the physics is cleaner in terms of having a huge separation of timescales between the fast regions and the slowest regions. But then, I mean, if someone could predict this, I don't know. This is really an open question. I don't know if you have a more precise.
No, this is kind of what I was wondering about. I mean, this is, yeah, as I said, this is not a propensity, but if the structure encodes this sort of thing, then and the recognition is successful at the higher temperatures, does it also work at these lower temperatures, or is there something really new that in these simulations now that is very different?
So I think the new thing is that the separation between the time scale is clear. I think now the question is whether this is encoded in the initial structure or not. So I think I tried to give a flavor as to what can be encoded, the first regions that start to relax, and then what is not encoded maybe is the facilitation. This is sort of a stochastic effect. So I mean, I'm afraid I cannot answer better this than this is open question. The hope would be that that the methods work better. If they don't work better, then I think it means something for the physics. It means that this pattern is not encoded in the structure. So I mean, this is just open questions. Yeah.
Yes, so about this, have you taken even a quick look at the ISO configurational, at least 2 clones?
Yeah.
Yes?
I
Because I
have.
would expect that the really blue regions, I mean, since they are attacked multiple times over your long time scales, I guess in a clone of the system, they are still very robust. I don't know.
Yes, I
Yes.
have. It would take. I can show you afterwards. It would take too much time to dig the figure up. But
Okay.
at this temperature, I've looked at the. I haven't run 2 months, but I looked at, let's say, I don't know, 10% of decorrelation, and I can tell you that some regions relax 100% of the time in the 30 ISO configurational ensemble that I did.
Okay.
But then, these regions start, but then I can show you the individual runs. Then the dynamic starts to spread in maybe different directions, or not all the same regions relax. So the question is whether
complicated.
this
It's
is
not-
better than here or not. So I would need to, one would need to quantify the
How much is
predictability.
deterministic?
But
Yeah.
this is one of my open questions. Is it more or less predictable? And I think that Gerhard will talk about this in his talk.
And by looking, the very blue regions that are far
Yeah.
away, I mean, are there still some constant stuff also?
Yes,
that
I
are-
would say that these blue regions here, so I couldn't look at what happens after 2 months. So this region here is really not going to relax. I would say that this is going to be the thing that will stay constant between runs. Exactly how the dynamics evolves toward this is not clear. But if there is something in the structure here that makes it extremely slow, I guess that this would be reproducible.
Okay. And sorry, can I ask one other question? Okay. You said that, I think you're right, that everybody should use this new area of temperatures to study these new physics that are accessible. So are you going to share the data?
I think yes.
Yes?
I don't know.
Amazing.
I mean, I'm happy to do it. I think that there's a question here. This takes a long time. It burns CO2 energy. If everyone does it on its own, then I think that it's a bit stupid.
If we use the data, we will cite you for sure.
I don't know. It's then it's a separate discussion about open science, but yeah.
All right, thank you very much.
Yeah, thanks.
And thank you again. Okay, so now we have a break until 4, and then we reconvene at 4. So there is some coffee and something to eat.
Learning is based on dynamic propensity, which is multiple. We've also tried it with single characters.
Okay, you have.
We've been trying to work with Patty Royal, where
Okay.
what we could do with experimental data. Experimental data is pain, so let's ignore that for a second. But with theoretical data, we can actually get, correlations go down, but we still get some decent
some good-
correlation
okay.
with single
Single runs.
With
Okay.
single runs, which
Okay.
is closer to, which is something one could imagine doing
In this
your
case.
kind of data actively. And what we also have seen in the past is that our correlations actually.
micro, c'est juste. Okay. Okay, so it's 4 o'clock, so we start the last 2 sessions of the afternoon. So we have Daniele Coslovich followed by Joerg Rottler. And Daniele will talk about dimensionality reduction of structured and glassy liquids as advertised aloud by Laura this morning.
Thank you very much, and thanks to Ludovic, Giulio, and Gerard for setting up this very nice meeting. So today I'm going to cherry pick a few of the arguments that have been put forth by Laura and also by Olivier, and I will try to give my point of view on that. And I'm going to tell you about the work that we have been doing over the last few years together with a former PhD student of mine, Joris Paré in Montpellier, and Rob Jack. And it's going to be a summary of a paper that we pushed last week on the archive here. And all the analysis in that paper, and also the one that I will show today, can be reproduced from scratch within a terminal. Just type in make all in a Docker container if you want. So for those who care about reproducible research, please have a look if you want. All right, so let me start with a bit of motivation. Maybe. Okay, and so my personal motivation for unsupervised learning was actually finding this. What is this? Yeah, I heard it. What kind of structure is it? It's an icosahedral structure, right? So this is a locally favored structure, okay? So if you look closely in your favorite computer model of a glass, you may find some local arrangements that are more symmetric, more stable than the rest, okay? And there have been reports of these kind of structures in Lennard-Jones mixtures, but also in metallic glasses, in colloidal suspensions, and so on. But one may still wonder whether this kind of arrangement is really different from the rest, from the bulk. What if it's not just a continuum of possible arrangements? All right. So in order to go through a definition of locally favored structure that is well founded, I would like to make first a bit of an history of how we got to these ideas. And I will start with a very naive, and I will call it Voronoi-based definition of locally favored structure. This is what we used long ago for Lennard-Jones mixtures. And the idea is the following. You start from a Voronoi tessellation, and you look at the signatures of the Voronoi cells around each particle. So this is just a sequence of numbers that characterizes the shape of your local arrangements of the neighbors around the particle. And then you go to low temperature and make statistics and check which signatures are the most frequent ones. And those are, for you, the locally favored structure, the ones that get accumulated by the supercooled liquid as you lower the temperature. Yeah, go. Since it's in the slide, we can.
Yeah, so when you do this on instantaneous snapshot, or is there a time average to have some kind of a reference position?
Okay, strictly speaking, I think those measurements were done on internet structures. But qualitatively at low temperature, it will not change much if you just took the instantaneous configurations. But you get, of course, a cleaner signal if you do some averaging or if you consider internet structures, so local minima. All right, so of course, this doesn't work always very well. It's known that Voronoi signatures are very sensitive to thermal distortions. You can get very different signature just because there is thermal motion. And also, you don't know what to do if you have two signatures which are about on par in the statistics. Which one is the locally favored structures? How do you distinguish them? So Paddy Royal has his own way of looking at locally favored structures. We heard about quickly in the talk by Laura about topological cluster classification. And what Paddy does is looking up an extensive database of possible minimal energy clusters of the system it has, and then making a statistics of all these possible arrangements. But because of the way these clusters are made, they can overlap with one another. They can be contained within one another. And so it's not easy to count them. So what Paddy does, he also looks a little bit at the dynamics of these objects. And in particular, he looks at the lifetime. And then he says, OK, well, the structure that has the longest lifetime is going to be my locally favored structure. So it seems like we don't have a robust, thermally robust, and a purely structural measure definition of locally favored structure. Okay? So this is my initial motivation to use unsupervised learning to tackle this problem. So we heard about bond orientation loaded parameters this morning. This is another way to characterize local structure that our community has used for decades.
I will quickly go through them because there are a few points that I would like to emphasize compared to what Laura has mentioned this morning. So this is based on a definition of neighbors of a particle that has some sort of sharpness. Okay, you say the neighbors of a particle are those that are within a distance which corresponds to the first minimum of the g of r. Okay, and those are your neighbors. Then you project this position on a unit radius sphere and make an expansion in spherical harmonics and then construct rotational invariance. Okay, this is the procedure, but it's based on a sharp definition of neighbors. And then physical intuition tells you that if you have a dense system, you should probably look at invariance of order 6, of order 4, and this gives you a descriptor of the local structure. Okay, and people have used that to characterize disordered materials and so on. Okay, again, so it's interesting to look how similar problems have been tackled in a community parallel to ours. And I'm thinking in particular of the hard condensed matter, material science community. Okay? And there they were also interested in smooth descriptors of the structure, but their interest was actually for fitting the potential energy surface and obtaining effective potentials that are very realistic and can also be coupled with neural networks. And one of the seminal papers in this context was this paper by Parinello and Beller that introduced some high-dimensional descriptors of the structure that can be used for neural network potentials. And then there were refinement and improvements. And for instance, I will talk a little bit later about these SOAP parameters, smooth overlap of atomic positions parameters, that were introduced by Gabor Shani. And there are many others. Okay? So one thing they have in common, and it's very different from the Q4, Q6 description that we saw before, is that all these objects are highly dimensional. For every particle, you can have hundreds of numbers that characterize the structure around them. But they don't care, because what they want is fit in the potential energy surface and get a reliable description of the local environment. Okay? But over time, they also started to try to learn something about the physics and chemistry of these systems by projecting these high-dimensional descriptors on a lower dimensional space. And they applied it to a range of system molecules, mostly crystalline materials. And this is the kind of map that they get. This is a reduced dimensional descriptor of the structure of your system. And you can recognize different regions in this map that correspond to different kind of local order. They sometimes look at amorphous systems as well, but I have the feeling that they don't quite know what to do with them. So for instance, here they look at an amorphous carbon thin film, okay? And then they check these low dimensional maps and they say, okay, well, there are some regions that are well separated from one another and they correspond to different coordination numbers. Well, this is not so surprising. You have a highly directional bonding system here, so it's not such a big deal. So let's see whether we can turn these ideas into something that can be useful to address the harder problem, I think, that we have in our community. So here I will again get back to the idea of unsupervised learning that Laura has introduced this morning. And in this context, we have a data set, which is composed by many data points. And in our case, a data point will be just a descriptor of the structure, which is a sequence of real numbers. Okay? And every particle will have its own m-dimensional descriptor. Then one key concept in unsupervised learning, as we heard this morning, is clustering, the idea that you may try to group these data points according to some criterion of similarity or proximity in some sense. Okay? This is roughly the idea. And you can get, you have different algorithms to do this kind of clustering. Actually, the workflow is quite sophisticated. You start from a descriptor, then you may pre-process your data, feature scaling, then you can reduce the dimensionality to get a lower dimensional representation, and then eventually do clustering. Okay? And a little advertisement. So Joris has written down a nice Python framework to deal with this workflow at a high level, so to say, so that it's easy to customize all these steps with just a few lines of code. It's an obsessively documented piece of software to my standards. Okay, so there's a nice tutorial. It's thoroughly documented to my standards. And it's also, I think, it's tailored for the kind of work that we do. It has the descriptors we use, the trajectory formats that we use. It's, of course, a young project, but if you want to contribute and have a look or find bugs, help yourself or get in contact with us. Okay, so So in the following, I will use this approach, and I will actually cut the workflow here. Okay, so since different clustering algorithms can give us different answers, so why don't we just look at the raw dimensionality reduction results without any clustering on top of that, and let's see what we can learn from this. Okay, so to start, I will just describe a little bit more our setup, which is the simplest possible so far. I will use as a descriptor a smooth version of the bond order parameters. Smooth means that here we add a windowing function that goes sharply but smoothly to 0 around the distance that corresponds to the first minimum of the G of R. Okay, so this is R cut, and this is our F function. Okay, this is necessary to smear the discontinuity that you will have with the bond order parameters if you have a sharp definition of neighbors. Okay, a particle leaves the first coordination shell, then the bond order parameters has a slight discontinuity. And I can show you later what happens if you don't do this mirroring. And then, of course, we construct a rotational invariance, and we get a descriptor of 8 numbers, the first 8 invariants, and we check that even if you go to, I don't know, 16, the results do not really change. And then we use the simplest possible dimensionality reduction technique. We heard about this morning, principal component analysis. This is simple, a linear transformation, so we understand what's going on. One piece of information that I would like to add is that the directions along which you project your data set are nothing but the eigenvectors of the covariance matrix. Okay, so the first principal component, direction here, corresponds to the eigenvector of the covariance matrix that capture the largest variance in your data set, and then you have all the other smaller principal components. Okay, so it has a simple interpretation in terms of the covariance matrix. And so what we will do in the following, we will look at the projections on the few first principal components in the hope that they capture the bulk of the signal. And to start with, I will look at my favorite benchmark. If there is a signal, I should see it here. I'm looking at the Van Strom-Lennard-Jones mixture. It's a simple mixture, which is known to have a strong icosahedral order. So let's see how these reduced dimensional maps look like in this case, where we more or less know what we should get. So this is the distribution of your reduced representation x1 tilde, x2 tilde. These are the first 2 principal components. And this is the probability distribution of those pairs, okay, for this system close to the mode coupling crossover temperature. Here it's instantaneous configurations, and here it's inherent structures. Okay. So this is the kind of map that also Gabor Chani was looking at before. So one first thing is that if you look at inherent structures or instantaneous configurations, qualitatively the picture doesn't change. Okay, so more or less we get the same kind of pictures, even though the balance of these 2 areas will be slightly different. So we can clearly recognize a central diffuse region here and a lobe that detaches clearly from the bulk. The same thing here, but this lobe is more populated. And if you cross this information with a Voronoi-based LFS, you will recognize that the lobe is indeed due to the icosahedral structures that are the locally favored structure of this system. So the method here seems to capture what we expected. There's a well-defined locally favored structure which appears as a lobe in this low-dimensional distribution of your reduced variables. These are the first eigenvectors of the covariance matrix. As expected, this eigenvector has a strong signal on the 6th order invariant and opposite signals of the neighboring invariants. So it again explains a bit what we have found in terms of icosahedral local order. Okay, so now that we are confident that the system works, that the method works, we can explore a broader range, a broader pool of computer models of glassy binary mixtures. And here we not only consider simple Lennard-Jones mixtures, but also more realistic models of metallic alloys like copper zirconium, as well as a model of amorphous silica here. So we have a range of very different binary mixtures. And as we go from left to right, we see some sort of gradient, some sort of change, progressive change. So what I see here is that in these 2 models, maybe there's a broad range of reduced features, but the distribution is more or less unimodal. Okay, so there's a single blob, a central spot, whereas in this other two, there's an additional lobe, and this is due to icosahedral order. And this is actually the same also for this copper zirconium mixture. So basically the same phenomenology as the Lennard-Jones mixture. And in the amorphous silica, you get a range here that corresponds to ideal tetrahedral environments, and then a diffuse area. I'm not sure if you can see, but there are many spots here corresponding to defects in the structure, like under-coordinated environments. Okay, so you can clearly see that there is one favored local structure and many, many defects. Okay, so from going left to right, what I see is that there are systems that are weakly heterogeneous, and in which, there is no well-defined locally favored structures, and systems that are more strongly heterogeneous on the right. Okay, to argue that it's enough to look at just a few principal components, here I show the captured variance along each of these principal component directions. Okay, and so we see that with a few, like 2 or even 1 principal component, we gather already a lot of the variance in the full data set. And there's usually a gap between the first 2 principal components and the rest. Okay? So it seems like it has a relatively low intrinsic dimension. And then it's also interesting to try to connect these reduced structural variables to physically motivated measures of local order. And so what we do is, for each principal component, we compute the correlation coefficient with potential energy, coordination number, a measure of how compact the local structure is, the theta parameter that we heard before, and also the LFS. And what we can see is that the first few principal components here, they tend to be correlated with these physically motivated measures. So in a sense, they found automatically these interesting fluctuations in the local structures by themselves. Another thing, again, to support this idea, you see that the LFS is always correlated to the first principal component, even in the Cobb-Anderson mixture. But here, the correlation is simply not strong enough so that these structures stands out from the bulk of the disordered local arrangements. Okay, so there's a weak correlation, but it's not strong enough to detach it from the bulk. So in this sense, it's not well defined as a locally favored structure. Okay. Just to motivate even more the use of these reduced variables, this is a comparison with the correlation coefficients that you get with the same quantities and the bare rotational invariants. And as you can see now, the correlations are spread over many more rotational invariants. So in a sense, the principal components aggregate this information in a very compact and meaningful way, I would say. All right. So we heard about this morning that there are different ways to reduce the dimensionality of a data set. I used the principal component analysis so far. What about a neural network autoencoder that Laura described very nicely this morning? So it allows us to get a reduced dimensional representation of the data that best fit the full data set. Okay, and so we ask for 2 variables, just 2 variables, x tilde 1 and 2 AE. And then we can compare it with a principal component analysis, the first 2 principal components. So this is the results of the autoencoder for the Van Strom-Lennard-Jones mixture, always the same descriptor. And as you can see, we get the same kind of picture, but just rotated, sort of. And every time you relaunch the autoencoder, you will find a different rotation. So the rotation is completely irrelevant. So what we do is rigidly rotate the picture until we get a maximum correlation with the same plot with principal component analysis. And when we do so, we see that the correlation is basically 100%, which means, yes, please.
What is the activation function of the encoder?
These are tangent. Yeah, it's the same setup that Laura described this morning. So we try to reparameterize everything to put ourselves in the same conditions as they did to essentially reproduce the results. And so, yeah, so it's actually maybe not worth the effort to really reparameterize everything because we get the same results essentially as PCA.
Because mathematically, if it's linear function,
No, it's tangent. It's hyperbolic tangent function.
so it's not enough non-linearity in the data, you will get this even.
Exactly. So I think this suggests that the data set is simply very simple. There are no complicated patterns in the data set that would require a nonlinear, sophisticated dimensionality reduction. That's it. Glass structure is very simple. All right, so this is one message, I think. Yes.
The output is the set of, I don't remember how many, but
Eight
descriptors.
descriptors, yes.
8 descriptors,
Yeah.
okay, and the bottleneck is 2.
Yeah. Yeah.
And you reproduce, how good is the encoder at producing the input?
Good, pretty good.
No, this is not what
No, it's another number. Yeah, I don't quite remember it, but it works pretty well. Okay. Right. So these were very small dimensional descriptors in the first place. Okay, just 8 numbers. What about these higher dimensional descriptors that the material science community is using a lot? And here I will present a little bit of results about SOAP. So SOAP, what it does, it starts from a smooth description of the local density. So the local density of each particle is microscopic, is mirrored with a Gaussian or with sigma, okay? And then this smoothed density is expanded in spherical harmonics, plus they keep into account the radial dependence of the bond order with an additional basis, a radial basis, G of n of r, okay, which allows you to keep much more information in your descriptor. So you can choose many different shapes for this radial basis, and here we simply follow the original suggestion by Ksani, which is to use this kind of sum of polynomials, okay? And this is our radial basis. Then you construct again rotational invariants, and keep in mind here you have small n, n prime, L, so you have many more numbers. So you typically get 200, 300 parameters to play with and to reduce dimensionally. And this is what we do. We do again a principal component analysis. We pick up the first 2 principal components and compare the maps that we get to those of PCA. And to my eyes, you get very similar, qualitatively similar results. There's a unimodal distribution here for the Cobb-Anderson mixture and a lobe for the Van Strom-Lennard-Jones. So qualitatively, you get a very similar picture. But I should warn you. So here you have one additional hyperparameters and one more parameter against which you should converge the results and max. And Ksani and co-workers claim that they have a principled way to find the right values of these hyperparameters, but honestly I couldn't understand which is the principal way that they refer to. If anybody can help us in understanding what they do in this paper, I'm very, very happy. What we did was actually scanning all possible values of hyperparameters. And I have to say that the results do actually depend slightly on the choice of these hyperparameters. But it makes sense because depending on the length scale on which we are looking at and the degree of smearing, you may get different results. So the results will depend on that. It makes sense. So there's no magic way, in my opinion, to find out automatically these parameters through an algorithm. You have to keep your hands on it. OK. So now that we have some structural variables, of course, we would like to see whether they can inform us on the dynamics as well. And here we'll go back to the idea of the propensity of motion that we heard about this morning. And I would like to add a few more informations. So one thing that Olivier mentioned this morning was that the dynamics is encoded in the structure, okay, because you have Newton's law and so on. But wait, you have the momenta. So the original intuition by Peter Harwell was the following. I take one configuration, I start many independent MD trajectories, and what he realized was that the heterogeneities that you get in the dynamics are different every time that you start a new simulation, slightly different from one another. So we should get rid of this dependence on the momenta if you want to make a connection between structure and dynamics. And this is where the idea started. So you take the configuration, run many independent runs, and then average the results of the displacement after some time over all these trajectories. And this gives you the propensity of motion. Second piece of information that I would like to emphasize, this is a way to characterize the structural heterogeneity that can be possibly reproduced from the structure of the initial configuration. Okay? So this is the key idea. All right, so we heard about this. So there is a lot of interest in trying to fit in the propensity of motion with structural data using data-driven approaches. This was pioneered by Andrea Liu and co-workers with the support vector machine. Recently, there have been more sophisticated methods like graph neural networks. And Laura this morning told us that using a simple linear regression plus this spatial averaging, we get results that are on par with this more sophisticated method. As we can see here, for the Cobb-Arnes and Lennard-Jones mixtures, which is one of the hardest bench cases for this kind of measurement, I would say. So these two methods currently set what I would say is the world record for the correlation of this model around the structural relaxation time. Okay, let's see what we can do with our simple unsupervised approach. So here are results separately for small and big particles of these two Lennard-Jones mixtures. I show the correlation coefficient between propensity and each of the principal components as a function of time, scaled by tau alpha. Also, the thick line is a linear regression, as Laura mentioned this morning, to the full descriptor. Okay? So I aggregate everything and try to fit everything with linear regression. And as we can see, around small particles, things are easy. Because with the first principal component, you already get essentially the bulk of the signal that you would get with a whole descriptor. So there's a very well-defined measure of local order that captures the bulk of the signal that you can get, at least with this descriptor. Things are more tricky around the big particles, where you see the correlation is spread and it's weak. It's weak and it's spread over all the principal components. And when you aggregate them together, you get something like this, which remains a weak correlation, I would say, not so strong as around the small particles. So there's a difference here. Okay? Now, perhaps using higher dimensional descriptors, we get a better correlation. And so to check this, we use the SOAP parameters. And these are these new lines, red and black. So the red line is the SOAP parameters within the first coordination shell, okay, using two orders of, let's say, one order of magnitude more features in this case. And as you can see, this really enables us to harvest more information, and we get a boost in the correlation almost everywhere, I would say, which means that even though there is no qualitatively new information in terms of the heterogeneity of the local structure, there is something that is relevant for fitting accurately the propensity of motion, which is indeed captured by these higher dimensional descriptors. So these two lines here are restricted to the first coordination shell. And we can go beyond. We can go up to the second coordination shell to see if it improves. And somehow consistent with what Laura has been telling us this morning, going to larger length scale allows you to improve slightly the correlation everywhere. Okay, so you get a better signal indeed up to the second shell. Keep in mind, these are correlation coefficients between individual particle propensities. I'm not doing any coarse graining, and I think there will be some talks about that later tomorrow. Probably with a bit more of coarse graining, we can get closer to the world record, which is here. We're not quite there. All right, so I think that's almost all. I think my conclusion is that unsupervised learning is a promising route to look at structure in amorphous materials and to provide a robust definition of locally favored structures. And one thing that we see, at least around the mode coupling crossover, is that there is a varying degree of structure heterogeneity in the models that we have studied. There are systems which have a well-defined locally favored structure which stands out from the bulk, and others in which there is no such thing. Okay? There are a few technical lessons that I've learned the hard way on the way. First of all is beware of discontinuous descriptors. So in the first round of analysis, we used the bare bond order parameters without any smoothing, and this is the kind of pictures that you would get. So essentially, you have this fingering, these bands, that you can easily track down to different coordination numbers. So basically, the algorithm just learns that you have partitioned your environment according to the number of neighbors, and it will find out these slight discontinuities and project them on the first component. So pay attention to that. Okay, so in my opinion, the fact that there is no need for sophisticated neural networks, at least for this class of system, is a good news because the results that we get are more easily interpretable. Okay, and keep in mind that these high-dimensional descriptors can be a pain to parameterize and to control. Okay, so this is what we have learned on the way. But still, I think they provide a good way to fit the propensity of motion data, and I hope this is the message that will pass. One key final word. I think we know that the propensity of motion is encoded in the structure of the initial configuration. So if you give me a black box machine-learned order parameter that I cannot interpret, and it's highly correlated 100% to the propensity of motion, I will have learned nothing. And I know in advance that there should be a correlation with the structure. So the key point is being able to interpret this result, okay? And so we need interpretable descriptors and transparent method as much as possible. This is the key point, I think. That's all. Thank you for your attention.
Thank you, Daniele. We have time for questions, and I need to work with the microphone or run.
Thank you. Thank you for the talk. It was very inspiring. Can we go back to the results on amorphous silica? You told us that you identified the tetrahedral structure, which is in silica at least is the smallest recognizable structure, but silica has more than that. It has ring structures.
Not on this length scale. I mean, this is the first coordination length. This is what we can see.
That's going to be my question.
I see your question, and I see it's an interesting question. Yes, so we can go beyond.
So the choice of this local descriptor is key to be able to find the correlation between the quantity we are looking at. For example, for local dynamics, maybe the first order descriptors function well, but for example, if I want to correlate it to plastic events, if I want to correlate it to local rigidity, I might need more.
Well,
and the question is, what else? And how to obtain these descriptors, these local
So why is it connected to silica? I think this is a general comment in the end.
Maybe, because I am working with silica.
Okay. Well, there may be a few specific aspects to silica, the ring structure. We haven't tried to go beyond the first coordination shell. It would be interesting to do. On the other hand, we know how to identify rings, right? So maybe it's good to stick to them. But anyway.
No, but that's actually my question. We have lots of well-known structural formations, what we use classically. Mm-hmm. Do we need to use something which we already know can be correlated? Or can the algorithm detect some kind of local descriptor which we have no idea about at the very moment?
The only thing that I can say is that I didn't plug any information about the notion of tetrahedrality in this representation here, apart from the fact that I know there's a well-defined first coordination shell. Mm-hmm. So that's the only information that I plug into the descriptor. Then the rest is just principal component analysis that shows that there is, let's say, one region corresponding to ideal tetrahedra and other defective structures. So I didn't plug in that information by hand.
So what you are saying that you would increase to second, third, you would be able to detect the rings as well? Or
I don't want to,
Okay, thank you.
Let's say, but coming to your other question related to plasticity, I think one thing that worked very well, and David maybe can confirm, is that plastic events are strongly correlated to the theta parameter that measure how compact the local structure is. And we see that indeed this is one structural measures that gets picked up automatically by this kind of dimensionality reduction method. So in a sense, PC1 will probably be also reasonably well correlated to the places where you have plastic events as well. So
the only thing for plasticity, what I'm not sure is that you have an input that leads to, let's say, a cat and a dog. Like for plasticity, if I'm taking my sample and I just rotate it by 45,
mm-hmm.
does it change your input or is it rotation invariant?
No.
Plasticity, and if you rotate by 45, it's not a cat, it's a dog.
That's
I don't know if it's easy to, for anisotropic question, can you have an input which is also taking into account the rotation? But I don't know if you can do
I don't know, but one can think about it, yes.
Okay, do we have a final question for Daniele? Yes.
Thank you, Daniele. Can you show the slide with the correlation numbers? I think it was the second to last slide. the where you had the world record and you were catching up. Yeah, so I think the performance on long time scales is quite good, but what impressed me most is actually, or more, is actually the performance also on the smaller time scales, because there the structural descriptors, for example, that Laura has, like they basically don't manage to fit anything. So do you know what you get right at these maybe onset of the relaxation, which is not in the structural descriptors that we have used until now?
So first off, I think if you look at the unsupervised learning data, they are similar to what Laura showed. So they go down, the correlation go down at short times. Here, I don't do any, let's say, dimensionality reduction. I fit the full descriptor. So I just throw more information about the structure. So it's a different kind of thing than what Laura has been doing.
But what kind of information is between the blue and the black one?
A good question. I don't know. The only thing I can say is that it's a bit difficult to interpret the outcome of these SOAP descriptor because it's very high dimensional. So even if I look at the first principal components and try to interpret them, it's not easy. So in the end, what I would have to do is to correlate them to some other physical measures of local order again. So these are black boxes. Yeah. These are highly dimensional, too highly dimensional, with a radial basis that is not easy to interpret.
Thank you.
Okay, so I'm not sure, Daniel, if that was such a good idea to call it a world record, because
well,
it's about to be broken 3 times tomorrow, so I don't know.
For this, okay, then good, good. But keep in mind, this is the Coban-de-Selena-Jones mixture in 3 dimensions. Well, wait. Without any coarse graining. So this is without coarse graining. Okay. Okay, cool.
No, 3 times I said. So.
But I didn't claim any.
Yeah, see, you will see.
Well.
So come back tomorrow for the world record. Thank you very much, Daniele. Thank you.
Oh, sorry.
Il est dans la discussion. Je m'en rappelle pas. Il est sur AISSAI, non? Je suis. Quoi?
Actually, let me just put this. Let's take it in my pocket. Anyway.
Okay, so while you're setting up, so the final talk of today will be given by Joerg Rottler from Vancouver, and you can read the title just as well as I can. So the floor is all yours to finish the day. Thank you.
Thank you very much, Ludovic. Thank you for having me, and thank you for staying for the last talk. This is going to be a description of an experiment, trying to see whether machine learning methods, fresh approaches if you want, can help us with some of the hard problems and difficult questions that Olivier explained to us this morning. I'm going to be looking at 2 systems, grain boundaries, interfaces in crystals, and also glassy systems. All the work I'm going to present was done by Sibash Soltani, who's a PhD student at UBC in Vancouver, and my collaborator is Chad Sinclair, who's also a faculty member at UBC. So we're going to be using a method that was discussed earlier this morning already, graph neural networks, and we'll connect that with a tool from statistical physics known as Markov state models. And I'll explain that a little bit more as we go along. So at this stage of the conference, I don't think I have to convince you that it's a difficult problem to link structure, dynamics, and also thermodynamics in highly disordered systems or in systems with many defects. And this is why we have come together to see if machine learning methods can help us out here. And the motivation for this is that we know that machine learning methods are very good in extracting structural features out of a complicated data set. And the question that interests us is whether those features can be linked causally to local mobility. And one of the concepts that was introduced, I would say, about 7 years ago that gave us hope that such an approach would indeed be fruitful is this idea about softness. And this is a classification of particles into slow-moving and fast-moving particles. So one has to train here a system. In this case, it's just it's this simple division into a hyperplane of fast and slow-moving particles. And if one does that, then one could, for instance, predict that fast-moving particles would be found predominantly at the interfaces between grains in a polycrystal or in a glass would agglomerate into clusters that are separated from slow-moving particles. Now, one thing that resonated with me really is that this method does not only produce pretty pictures, but there's more that one can get out of this concept. For instance, one can inquire into the temperature dependence of the probability of a particle with a certain softness S, and then one finds that it has a simple Arrhenius form, so one can ascribe an energy barrier and a prefactor to that, and one can associate that with the degree of softness. So this establishes quite robustly, I think, that there is a relationship between structure and dynamics. A related problem that we face in material simulations is accessing slow dynamics in general, in particular at low time scales. And this arises, for instance, in the mobility of grain boundaries, which is a very important phenomenon in materials processing. But grain boundaries are extended defects, they're interfaces, and they move very, very slowly. And studying that with molecular simulations is therefore a great challenge. One would ascribe this or describe grain boundaries usually by a coefficient called the mobility, which is the proportionality coefficient between grain boundary velocity and the thermodynamic driving force or the driving pressure, if you want. And in glasses, it was mentioned many times today that the hallmark of the glass transition is that structural relaxation times increase dramatically upon cooling, and phenomenologically this can be described by this so-called Vogel-Furcher law here, which predicts sort of a divergence of the relaxation time at some temperature, T0. So this is very difficult to explore at low temperatures, and what we want to do in this talk is it possible to come up with a method that simultaneously finds the slow variables, finds their structural features, but at the same time also gives us information about the dynamics, right? I mean, the softness method is very nice. It obviously finds structural features, but not directly information about the relaxation time scale. So that's going to be, and in doing so, can this also help us with this slow time scale problem? So in some sense, what I would like to do is a dynamical coarse graining. So simplify the system, try to come up with a method that accesses the slow processes from short simulations, and in doing so, provide a connection between the some coarse-grained collective variables and the macroscopic kinetics, which is the mobility of the particles or of the grain boundaries. And the tool we're going to use for that are the Markov state models. Now, some of you might have heard this term before in the context of molecular biology. These methods have a long history, and have been used a lot to describe conformational changes in protein folding, where one tries to understand how the polypeptide visits different regions in the free energy landscape and ultimately arrives at its functionally folded state. Now, much of this work here is based on and following the work of Frank Noé and collaborators who have developed these concepts over many years. And we are basically trying to transplant this method from the sort of field of molecular biology and see if it can help us also with some of the systems, some of the condensed matter systems that we're interested in here. Now, what do we want to do? We want to come up with a low-dimensional model of a dynamical system. There's two things that we have to do in principle. The first thing is that we have to come up with some sort of embedding. So we have to take our 3n coordinates of our particles, and we have to map this onto a lower dimensional feature or latent space. So the second thing we need to then do is we need to come up with some sort of propagator that advances these low dimensional coordinates in time. This map we want to be linear here. And how do we find these two descriptions here? Well, so this K here, this is can be interpreted as a matrix of probabilities. So if you are in a system, if you are at state I at time t, then this is the conditional probability to find the system in state j at some later time t plus tau here. So finding this k propagator is something actually fairly straightforward, just from minimizing a least squared error. One can come up with a formula that relates this to the covariance matrices of these latent space variables. A more difficult problem is to find this embedding. And much progress has been made in this field by the introduction of this variational approach for Markov processors, which is a variational concept that prescribes us with a suitable loss function that gives, if optimized, the optimal mapping in that parameter space. And one can use neural networks or train neural networks on this loss function to perform this mapping for us. So the idea is conceptually illustrated here. So we have two positions, x of t and x of t plus tau. These are the 3-dimensional coordinates of your molecular dynamics systems if you want. We want to project this onto a lower dimensional system here, denoted by y of t. And in this space, we're then going to perform the dynamics using this Markov state model. So just a very quick slide on some details on this. So the dynamical system is described in full detail with the molecular dynamics here. The embedding then takes us to the low dimensional space here, and the propagator k advances these variables here through a linear map. So these are the formulas. You don't need to pay too much attention to the details, but just that you know that this is what's under the hood. So one considers these covariance matrices here, and this is this loss function that emanates from this variational principle that is optimized in the course of training this method here. This graph is trying to illustrate to you what the processing pipeline is. So imagine two configurations. Here in this case, it's the example of a grain boundary where we have an interface here that you can see in red here at two different times here. The first step that we do is to use these graph networks to come up with a local description of the particles that was described quite extensively by Laura this morning. One uses convolutions to sort of spread out the information over a larger range in space here. Then one does some sort of pooling operation to collect all this information into a large feature vector. And finally, one optimizes the network using this variational loss, using this variational score here. So the way this works is you obtain a molecular trajectory, and you take in the entire dynamical information of this trajectory. So you take these snapshots separated by the lag time tau, and after you've looked at that whole trajectory, you have produced this embedding here, and now you can study the properties of this system here. So none of this is particularly original to us. It was actually introduced again by Frank Noy's group here about a few years ago, and then adapted for condensed matter systems here in this publication by Xi et al. There was a question?
Yeah, I'm hung up on something very basic. So, which is I thought with the Markov state models you don't have that memory. You're just doing from t to t plus tau, but you're saying. Right.
There is no memory in the Markov state model, yes.
But these are systems that have a lot of memory.
We can make the lag time tau large enough that they become memoryless. I'll show you in a minute.
I see. So it's many times the relaxation time.
Well, not many times. Less than one is enough. You will see. Okay. So, was that the question? So yes. So we are seeking a model that is memoryless. So the probability depends only on the time t and not on the prior history. And this is possible to do for the two systems that I was about to describe, the grain-brownie system and the truly disordered system. So if you wouldn't mind hanging on for a couple of minutes, hopefully it will become clearer. So, okay. So, but maybe I should describe a little bit more for the audience what a Markov state model is. So you could write it down in this way. So let's consider a state space vector P, which is the probability of finding the system at a set of states. We're also going to have a propagator K, which is just a matrix here, which is a linear map here that advances the state space vector from time t to time t plus delta t here. So all the information then about the model is encoded in this transition matrix here. So Now, the simplest case that's conceptually easy to understand is a two-state model. So we have state 0 and state 1. Well, the only information that we then need is the transition rate to go from state 0 to 1 and back from 1 to 0. Those are the only non-trivial entries in that matrix here. The total conversion timescale is just the inverse of the reciprocal of these rates. And one can also obtain this from the non-trivial eigenvalue of this matrix here. And you see here that it depends on delta t, but as Andrea pointed out, for a Markovian process, there should be no memory, so then the timescale should not depend on this particular time here. So we have to make sure that we coarse grain sufficiently enough so that this memoryless dynamics is indeed obtained. All right. There is also interesting information in the eigenvector of this matrix, and that is the ultimate equilibrium distribution that this Markov state model would evolve to at long times. And if you would like, you can think of all of this in an energy landscape picture. So if you ascribe two values of a free energy G0 and G1 to our two states, and we imagine some free energy barrier in between with magnitude G star, then we can just simply write the transition rates in an activated fashion here, in an Arrhenius form here, and the ratio of the forward and backward rates is just related to the free energy difference of the two minima. Okay. Now, this is a two-state model. We can go more complicated and, of course, do more than that. But conceptually, I think that is the simplest thing to understand. All right. Now, the first case I want to discuss is the grain boundary example. So just a reminder, we're interested in this mobility here, which is linking the velocity and the driving force. In a conventional molecular dynamics calculation, you would just run this boundary at some, let it fluctuate at finite temperature, and you just measure its mean squared displacement. And if this is linear, which is what's typical thing to expect, then the boundary is just diffusing. You can extract the diffusion constant, d, and using a Green-Kubo relation, you can convert that into a mobility. All right, that's a standard approach. Now, what we're going to do here is to look at three so-called high symmetry boundaries in BCC iron. This is mainly because my collaborators are physical metallurgists, and, well, they want to make steel, so they have to look at iron. But this is actually not terribly important. If you don't know what a sigma 3,111 boundary is, don't worry. It's not a detail that's not terribly important. You take two grains, you rotate one against another along a crystallographic axis, in this case the 111 axis, a certain angle. This is a picture of this set sigma 3,111 boundary. You can see this is that there are two grains here that meet at an angle. You see the interface here where the grain boundary is occurring. This is a highly symmetric boundary, and the degree of symmetry is described by this sigma parameter here. All right, so we're going to look at that, and let's see what our Markov model can predict for this. Here we are doing a four-state model, and you can see a color assignment on these particles. This is a picture of the thermalized boundary at finite temperature here. State 0 in our model, it turns out to be particles or atoms in the crystal state, whereas the other states that are occurring here are grain boundary states, so those are the defect states, if you want. Okay, so all right, maybe not so surprising, our Markov state model finds the defect. And it identifies several intra-boundary states, which appear to have this layered structure here, which is related to the symmetry of the boundary here. This is a picture of a different boundary, the so-called sigma 11 one. It's still a symmetric tilt boundary. You see that the angle of mismatch is slightly different. And these, again, our model finds for state 0 the crystal state, and the other three states are the defect states, the grain boundary states. And we have a different partition now of the grain boundary because of different internal structure. All right. Now, this hopefully will answer Andrea's questions about the emergence of Markovianity. So what one does in this method is you systematically increase the lag time between the two snapshots, and you measure the implied time scale. And then you watch and hope for a convergence, a time at which the observed time scale no longer depends on the lag time. It shouldn't, otherwise the method doesn't make sense. And at that point, we have coarse-grained the system sufficiently enough in time so that the dynamics is indeed memoryless and can be described as simple. I'm sorry? The different colors here correspond to 3 different time scales. So we have a 4-state model, and there are 3 time scales involved in this thing. There's a hierarchy of time scales that emerge here. And in this case, more or less all 3 of them plateau at about the same time, which is nice. The black one is just the horizon. It's just where it's just the time scale equaling the lag time. So it's just the simulation horizon, if you want. So you can see that this crossover here occurs at a time which is much larger. So the implied time scale, 10 to the 4, is much larger at this time than the actual simulation time, which is about 2 times 10 to the 3 or something like this. Okay, so this is what we do here. So now the next step is what one can do is, maybe I show this real quick, is one can check that the model actually, one can check for how well the model, the learned model predicts longer times. And the Markov state community calls this a Chapman-Kolmogorov test. So essentially, if the dynamics is linear, then if you repeatedly apply, if you apply the propagator n times, you should get the same result as just observing the system, well, n times the lag time. And indeed, this does work out quite well for the different transitions that occur in the model. So this is a sanity check that the model does make sense. Now, what else can we learn from this? Well, you can look at the eigenvectors. And you can see, then infer information about the dynamical processes that are represented from these different time scales. So if you look at the eigenvector that corresponds to the slowest time scale here, then you can interpret this as fluxes. So this is telling you that there is a transition from state 0 into the other 3 states. And this is simply the conversion of an atom from the crystal state into the grain boundary state. So this should ultimately correspond to the overall translation of the interface. And then there are faster processes that correspond to intra-boundary transitions. For instance, you can see that the next one is a transition between states 2 and 3, between states 1 and 2 into state 3. And then the fastest one is between state 1 and 2. So you gain information about relaxations sort of that occur inside the boundary. And if you plot these 3 timescales, we see that they are more or less following an Arrhenius law, which is probably to be expected for this kind of systems. This graph now shows you that the slowest timescale of the model indeed describes the overall translational mobility of the boundary. The open symbols is the mobility obtained from the conventional method that I described before. So you do a brute force molecular simulation, and you actually watch the boundary move, and you infer the mobility from this. And the filled symbols are the mobility that would be inferred from our Markov state model. Here one has to as an input, define the width of the boundary. That can be done. And then you can see that these 3 boundaries here more or less agree in terms of their mobility. So indeed, we can capture the macroscopic mobility of this system using this method here. Why is this interesting? Because we can now explore lower temperatures with this method, where the direct MD simulation is much more difficult. And here you can see that there's actually different behavior that emerges. There's obviously a different regime where there's still activated behavior, still Arrhenius, but it's a different slope, a different energy barrier, and a different prefactor here. So this would be very difficult to see with the conventional method, and it can be found here with this Markov state model.
At which temperature was the model learned?
Okay, good question. So this actually does not really, it turns out that it does not really matter. So we've checked different temperatures, and it turns out that you can learn at one temperature and apply at other temperatures.
Well, but not on the top 3, right?
Yeah, well, okay, so even there we get a good agreement. So you can learn.
So they are accessible with direct simulation.
So okay, so we weren't actually okay. So we were able to train the model in this temperature regime, but we are not able to calculate the mobility using the direct brute force MD method.
You need much more statistics.
That's exactly right. So that's exactly right. So we can obtain the time scale, but we cannot do this direct calculation anymore. That's right. That's right. All right. So maybe the moment you've all been waiting for. Maybe you don't care so much about grain boundaries. Maybe you only care about glasses. Finally, so I'm waiting for Ludovic to kick me out here, but we're getting there. And okay, So let's see what this method is going to do on our favorite, beloved glassy systems. And what other system could we choose to study than the celebrated, famous, infamous 80-20 binary Lennard-Jones mixture, aka Cope-Anderson model. Not the best glass former that exists as we know, but sufficient for our purposes. All right. Here we are going, and so for the remainder of this talk, I'm just going to consider a two-state model. All right, somewhat resonating with Laura's discussion this morning about her mapping of from the autoencoder. Okay, so what do you see in this graph here in this Arrhenius representation? First, please focus on the open symbols. The open symbols is the time scale that is found from this Markov state model. And you can see that there is some sort of there's a bit of an Arrhenius law at high temperatures, then there is a faster than Arrhenius rise here, and then here in the low temperature regime, where the system is in principle no longer equilibrated, we observe a different behavior here with, again, an Arrhenius type of law here, with a different prefactor here, but a somewhat slope that's not too different. Now, one thing I want to emphasize is that, yeah. So in a two-state model, if I go back to my slide here, in a two-state model, I only have a conversion time scale, and it is this time scale that is being plotted here, right? So you can interpret it as this, or you can interpret it, in this picture.
But it's extracted from the data directly, no? And then you plug it to your Markov.
So the training algorithm provides us with the matrix K and the embedding, and from the matrix K, we just read off this time scale, right? This is how this works. So this is a prediction from the Markov model. Okay.
And the embedding is only two states.
That is a choice that we made. That's an input parameter.
Is the per particle descriptor, right? Or is
so the Markov state.
The environment of a particle, and then you assign to this particle two states.
You will see in a minute what the map looks like. But yes, that is what will happen. Okay. That is what will happen. All right. Let's go back to this graph that we all understand here. The first thing I want to emphasize is that because the dynamics is linear in the Markov model, only a short trajectory is needed to actually measure this Markov state model time. So these times get quite large here, but you it's sufficient to simulate a relatively short period of time. The next thing I want to point out is that the time scale that we find here does not seem to be just the conventional alpha relaxation time, which is what is usually calculated, and we have seen all day being discussed here. So the alpha time was extracted using the standard definition. We calculate the decay of the self-intermediate scattering function, watch it, the decay to 1 over e, and read off the time scale. So the same quantity that you've seen all day. And okay, it has this, can be fitted with this VFT law, it's been many times here. And, but you can see that it is generally smaller than this MSM timescale here. And the inset, which carries the most important information, as always, shows you the ratio. Then it shows you that it's actually a non-trivial relationship between these two timescales here. All right. Now, we can also do this Chapman-Kolmogorov test here. We compare the predicted timescale to the actual dynamics here. And if this graph here shows you again how this Markovianity emerges, if we do this, look at this implied timescale at high temperature, we see a quick saturation occurring here at a timescale that's about the vibrational timescale. And if we do this at low temperature, and this maybe, hopefully, will answer Andrea's question, at low temperature, of course, it takes longer to reach this plateau here. This is, you can see here simultaneously the decay of the self-intermediate scattering function, and the crossover occurs roughly at the relaxation time, but certainly not later. So we can get a memoryless dynamics if we coarse grain to a time scale that's just a bit less than the alpha time. Does that answer your question, Andrea? So this is what happens in this system here.
Yeah, I'm just confused. I'm trying to put it together with what the pictures that Camille was showing earlier, which showed those very non-mobile regions persisting many, many times the relaxation time.
Well, I'm not saying that we'll see how long it takes for the mobile regions to. It depends what you mean by mobility. So let me describe what this picture will do. But I guess one statement is that if you apply this machinery to this glass forming system, then one can achieve a dynamics that should be memoryless at a time scale that's of order the alpha time or less. So that's the conclusion that comes from this.
You've seen pictures of what the system has done by this time, and it's essentially not relaxed. So how can it be at the same time?
That's the process that comes from it. So let's understand a bit better what we actually find here. Okay, so all right. So and again, keep in mind that the implied time scale is larger than the alpha time, right? So the Markov state model is doing something much more slowly, right? This is just a time scale at which this method will enable you to come up with a memoryless dynamics in this simple two-state space. All right. So that's what this does. Okay, so maybe I skipped this slide. This is just showing you the transition rates. Forward, backward rates are the same. An interesting feature is actually this bottom panel here, which is the ratio of the eigenvectors. And what you can see here that this ratio is independent of temperature. You can interpret this as the free energy difference between the two states in the Markov model. And if you find this to be temperature independent, then this suggests that the free energy difference is mostly entropic. So that's an interesting observation that one can make in this model here. All right, now let me show you a movie, or first a picture of this model here. So this is an assignment of the state variable to a particle. It produces a heterogeneous map. We get red and blue clusters here, according to the probability of being in one state here. So some heterogeneity is immediately picked up by this model here. And now I'm going to let this evolve here a little bit. And what you can see is the flickering. The duration of this movie is about 2.5 times the Markov state model time. And that is certainly enough for this map to decorrelate. So if you focus your eye on one of the blue or red clusters, you will see that they melt away in the course of the simulation, right? So this makes sense because if you evolve this Markov state model over several times its own intrinsic relaxation time, then you would expect it to lose its memory. Okay, so this is what the model will do. This is a state assignment here. Okay, so now of course the million-dollar question is, what is the meaning of these colors? Is there some physical interpretation of this? Or what do we make of this? In the grain boundary case, we knew where the defect was. We got some interesting information, but we don't actually know what is this. So our student, Sivash, worked very hard, and what he found was that, maybe we can skip that part in the interest of time. What he found was that these colors, or the map produced by this Markov state model time, corresponds very closely to a map of local Voronoi volumes. So you can see this here in this graph here. On the right-hand side, this is a Voronoi construction where you just ask for the optimal local tessellation of the system. On the left-hand side, you see the same Markov state assignment for the same configuration here. And with the bare eye, you can make out the similarities between these pictures. And middle plot just shows you the sort of a parametric plot of the local Voronoi volume of a particle versus this probability of being in that state 0. And you can see the correlation is linear. You can calculate a Pearson correlation, and that all of this points to the fact that this model seems to be latching on to the local volume of the particles in this system. Why exactly it does that, I don't know. Maybe it is trivial. I would love to hear your thoughts.
Because local density is it's the hydrodynamic field that remains at long times when you have lost all the structural relaxation.
So for you, it's obvious.
For me, it's a bit obvious.
For you, it's obvious. Okay.
But it's good.
Okay.
It's nice.
Okay, that's good. All right. So indeed, I mean, we have a method that we want to set out to find a local hydrodynamic variable, and so then it should ultimately recover things that match the intuition. Okay, so so that's what we found here. I thought it was interesting, also because there are ideas in the literature of the glass transition that invoke the notion of local density of volume as an explanation for some of these dramatic increases in relaxation times. What we found in our model here is that there's an entropic difference between the states, and if these states are indeed Voronoi cell volumes, then one would conclude that these different cells are basically different, or that the only difference in free energy comes from entropy. And my understanding is that this is kind of the picture that was painted in the 60s and 70s in these free volume type theories of the glass transition. We have way more sophisticated ideas today, and I certainly don't want to advocate that this is a tremendous a new solution or the ultimate answer to this. But I thought it was interesting that this machine learning Markov state model points us towards the importance of local density fluctuations. So maybe that's the message from this slide here. So, okay, I'm debating if I should show this slide here now, because there have been all these discussions about world records. And I think I will show it to you. Our interest here was actually not to come up with a particular prescription of the local propensity. We did not set out to train our model onto this property. But since there have been several papers that looked at this particular quantity, we thought we simply calculate the relationship between our newly found state map, also now equivalent to the map of local Voronoi volumes. And we've done this as a function of as a function of lag time, delta t. Now, I think it's been explained to you now what the local propensity is. You see here that all these curves here to obtain different temperatures reach a maximum. And what I want to point out to you is, however, that this maximum occurs not at the alpha time, which is what was found in studies like yours and others, but at a much later time, which corresponds to this Markov state model time. And that is the decorrelation time of the Voronoi volume map. And Daniele seems to disagree, or?
I agree. It's simply that this is the maximum that many people found with the local density at a long time.
Yes. Yes, that exactly. There is all the yes, exactly. I believe there is a 2014 paper even from Paddy and so. Yes, exactly. So I think this closes the loop on that thing. I think that is consistent with these earlier type of things here. So so we have this time.
Yeah. The questions, and he can finish because we are
anyway, well, I'm almost done. So well, that's part of the discussion. So all right. Well, I think this actually is bringing me to the end here. So we wanted to see. If this approach, graph neural networks combined with this Markov state model, can tell us something interesting about these complex condensed matter systems. I think it's an interesting aspect is that we get simultaneous access to dynamics and thermodynamics. Because this model is linear, short trajectories are enough to infer a time scale. One does not have to wait for the correlation function to decay all the way to 1/0. In the grain boundary case, the timescales that emerge relate to the actual mobility of the interface. In glasses, we find a timescale that seems to correspond to the relaxation of local Voronoi volumes. That tends to be larger than the conventionally discussed alpha process. And there seems to be, so I guess as Daniele pointed out, the hydrodynamic variable that emerges here does seem to be related to free volume or local density fluctuations. So I guess that's what I wanted to tell you. Thank you for listening.
Thank you.
Just the previous slide, I didn't get, it's the correlation between what and what?
So this is the same type of map that was discussed in several talks today. So this is the Pearson correlation between the map of the states, so a map like this, okay, and the map of a dynamic propensity. So one calculates for a given lag time, delta t, the dynamic propensity map, okay. Of course, it depends. And so then you get a map of the propensity, and you just correlate it with the map that emerges from this Markov state model, okay. The probability to observe your system in state 0 or state 1 if you wish, right? And so you see that this changes as a function of time and reaches a maximum when the lag time used to calculate the dynamic propensity equals this time scale that we found in the Markov state model. Does that make sense? Yeah? this is similar to what was shown by Laura, and I believe also by Daniele, except for that their correlation, their maps would, as far as I understand, peak at the alpha time itself, and then would disappear. So here we have something which is more slow, which is slower.
Other questions? Sylvain? No? Okay. Andrea?
I'm still confused. You have two states.
Mm-hmm.
They are states of different Voronoi volumes? Is that what you're saying?
No, so you take, I mean, you have two states, so then, of course, the probability, okay, we have P and 1 minus P is trivially related, right? So so this is a map of being in state 0, probability being state 0 if you want, and on the right-hand side is just the map of local Voronoi volumes. That's it, right? So these states seem to correspond to these local density things, local density variation.
I still don't get.
Well, that's what what they are. So a cluster. So the cluster the cluster of red is a cluster of small Voronoi volume. The cluster of blue is a cluster of large. So this is what the correlation graph at the bottom shows you, right? Small Voronoi volume, small probability to be in that state 0. So the method does pick out as the slowest variable these local volume fluctuations here. So that emerges from this machine learning approach.
Yep.
Mm-hmm.
Yeah, so I have two questions to relaxation timescales.
Mm-hmm.
One is more general because I'm coming from this biological system
Mm-hmm.
community, and usually what people say in biological system community is that Markov state models actually overestimate the biological timescales. So the timescales which are predicted with Markov state models are faster than those which are typical for biological systems. So it just as a comment to
Okay.
you. So it's typically what we all hear in this community.
I don't know the literature well enough to say, and I don't know. So you're saying that there should be a general overestimation of these
so
timescales.
the processes are a bit faster than they are in biology. So this is in biological context.
So if one, so there are the studies that I'm aware of. Is this so the timescales you're referring to are experimental timescales or computational timescales?
Experimental timescales.
Okay, I mean, I guess what can I say as a computational theoretical person then, right? My understanding is that if one looks at a comparison of the brute force calculation from an MD simulation and these Markov state models, that one can find a pretty good agreement on that. The real protein folding thing, but that's probably a criticism that one, or a comment that has to apply to atomistic simulations of protein folding in general. So, yeah. So then one can start talking about force fields and things like that, I would think. But
and the second more practical question, when you train your model, you make a decision on a tau at the beginning because you train your data with some interval.
Yeah.
And you train the data from different temperatures. So do you use different taus for different temperatures?
So that at any given temperatures, you use a particular tau. That's right. So the lag time, of course, changes. I mean, in fact, you can see this here in this graph here, which compares two different temperatures, right? One is the fluid temperature here. So so if you look here, so 1 in these units is fluid, and you can see here that this time at which you reach this plateau is essentially a 1 in these units here, right? Whereas here we are in the glassy regime, and the time is many orders of magnitude larger. So yes, this lag time, of course, rises as the relaxation time of the system rises, and that is intuitive, that this should indeed happen. Yes, so that then changes.
So do we have more questions for Joerg? You didn't say anything about the aging regime, where instead the relaxation time seems to be quite different from probably the extrapolation. So what do you have to say about this one?
So in the aging, so here the glass is no longer in equilibrium because we're not using a swap or anything. It's just a brute force MD simulation here. So if one were to let this glass age and repeat this measurement, one would find a different time scale. So the Markov state model time scale will become history dependent, just as any other observation time scale that you would measure from your self-intermediate scattering function decay, right? And this aging will, of course, continue until the glass would, if it could, be observed all the way out to equilibrium, right?
And again, your model is converging and it's becoming Markovian on short time scale while it's aging.
So it can because you should imagine that even though you don't equilibrium, the aging dynamics is slow on the time scale you need to actually observe to actually measure, to make the measurement with the Markov state model. So that separation time scale you need to have, right? So of course, if you have if your system is changing so quickly, even during the time scale of that you need to observe it, then of course you get some nonsensical result here. But this is not the case here. So the glass is already, so our cooling rate is slow enough so that the dynamics, although it is aging, it is slow compared to the time we need to measure that. So I view this really as an instantaneous snapshot of the relaxation time here. If you want, Ludovic, you can alternatively directly measure the decorrelation of the Voronoi volume. You can make a conventional correlation function for this object, and that is simply becoming waiting time dependent. It depends on T and TW, just like any other correlation function you could come up with and observe. So that's I think perfectly all right. And then and of course these things here depend on the age of the system and will eventually keep on increasing if you were to keep on equilibrating the glass. Does that make sense?
A little bit. Yes.
A little bit. Oh, I'm in trouble now. Anyway, never mind.
Thank you very much.
Okay. Thank you very much for listening in the last talk of the day.
We have, I think, invited speakers have just received an email about food, but that doesn't concern the other people. Please answer to that email, then we can organize everything. And we start tomorrow, same place, 9 o'clock. Thank you very much.
Okay.